Hello friends, in this video we'll be looking at syntax analysis. It is also called as the parsing phase, which is the second phase of the compiler, and you know that the first phase of the compiler is the lexical analysis, which is going to identify the tokens of the program, and it produces the stream of tokens. Once you produce the token stream, that will be taken as input to the syntax analysis, and it will produce a parse tree. Okay, now we are going to look at the syntax analysis. If you are going to observe the syntax analysis, it's going to be one of the important topic for whole compiler design. The weightage of the syntax analysis, you can predict 70 to 90% of the compiler design questions will be asked from syntax analysis, and that has been proven in many years. Okay, we have learnt the lexical analysis. Now we are moving to the syntax analysis. Then later on we'll be learning the SDTs, intermediate code, and code optimization. Then what is the syntax analysis? The syntax analysis is syntax analysis. The input to the syntax analysis is the token stream, which is simply looks like a string, right? One string is given to the syntax analysis. The string is actually a program, whole program converted to a string, and that string will be given to the syntax analysis. What is done by the syntax analysis? It will try to produce the parse tree if there is no syntax error. In case if there is any error, it will produce the syntax error. It will report to the error handler. Right. During this syntax verification, it uses a symbol table to identify or to look at the tokens in the program. Right. It has the sequence of tokens and it looks into the symbol table. Already those entries are made by the lexical analysis. Anyhow, the symbol table is used by all the phases of the compiler to know the information about identifiers and its attributes basically. Now, what is there in the syntax analysis, right? The first thing is syntax analysis is nothing but the verification of the syntax of the program. So how it's going to be verified the syntax of the program? We have various topics to learn, like you have context-free grammar, CFG, context-free grammar, which helps us to understand the syntax of the programs. What is there in the CFG? In CFG, you will be learning how to generate a program, nothing but how to generate a token stream, nothing but how to generate a string. So we are going to learn like something like that, how to derive a string, derivation of a string. Once you know how to derive a string, you will move to very famous types of grammars, ambiguous and unambiguous. CFGs. Then we'll be learning about context-free grammars, like how to eliminate a left recursion in context-free grammar. In case if you are interested to learn simplification of context-free grammar, you can learn how to eliminate null productions, unit productions, and then useless productions. But I'm directly going for elimination of left recursion. These things will be used in the future for parsers. Other one is left factoring. You need to convert grammar into different forms. So these algorithms are going to help us, like how to eliminate left recursion, how to do the left factoring. These things will help, will be helpful for the future in parsers, like top-down parser and bottom-up parsers. Fine. This is the first topic. We'll learn about the basics of the syntax analysis. For that, you require a context-free grammar. Once you learn the context-free grammar, we'll move to the top-down parser, as well as bottom-up parsers. We'll go for bottom-up parser. That's our interesting topic in this syntax analysis. So both are important equally. Sometimes they will be giving you grammar and identify whether it is ambiguous or not, whether it is LR1 or not, whether it is LL1 or not. So you require to identify it. So in this top-down parser and bottom-up parser, we will be constructing the tables, we'll be identifying the grammars. We are going to do a lot in that second topic. Okay, now to do this, first you should know what we are doing here. I told you we are verifying the syntax of the programs. Then what do you mean by verifying the syntax of the programs? You might be written many times the C program or any high level program. If you do some mistake, then compiler might produce errors. Among them, the one type of error is the syntax error. I already explained some of the lexical errors in a previous lecture. Now in this lecture, I'm focusing on the syntax errors. What is that syntax error? Okay, so I want you to understand what is the syntax error. What do you mean by syntax error? Okay, let me talk about the syntax error. You might forgot to end with semicolon, right? The one example, something like you have written x is equal 10. Will it be the right program? Will the compiler understand properly? If compiler anyhow analyzes, it understands there is a mistake, but is it a valid program? Is it possible to execute? The compiler will not allow to compile this code because this is syntactically wrong. There is a mistake in this line. There is a semicolon. You have not written the semicolon at the end of the statement. So this is definitely a syntax error, right? I'm just saying that what are the possible syntax errors? Sometimes you might be calling the function, but you forgot to close the parent, that you forgot to mention the closed parenthesis and you put the semicolon. That means this is not a proper code. And when you have the open parenthesis, then there should be closed parenthesis to balance it. So some of the balanced parentheses or square brackets or curly braces, and all of them are going to be verified in syntax. It is also syntax error. What else you have? The different kinds of statements, like you have the if statement and you forgot to mention the condition and you assume that the compiler will evaluate, but when it understands, when it trying to convert into the assembly code, it while analyzing the code itself, it finds a mistake. There is a syntax error. It's expecting some condition inside this parenthesis, but you missed it, so it will generate an error because it maintains a grammar to generate it. If grammar can't generate, that means it has an error. Okay, so there are various such errors are there in programs. Okay, syntax oriented programs, but it will not analyze the meaning of the program. What do you mean by meaning of the program or meaning of the code? Suppose you have written properly this code x is equal y semicolon. This code is syntax. This code as proper syntax. There is no issue with the syntax here, but there might be an issue with the types. If y and x types are not matching, compiler may produce an error. That is very important. It's a semantic analysis job. What a syntax does and what semantic does and what lexical analysis does. What lexical analysis does, it is trying to group the tokens. It is trying to group the characters into tokens. Like it's going to understand, okay, x is equal to y semicolon. That's the job of lexical analysis. It does the four things in this sequence. And once it understands the four tokens here, then syntax analysis comes into picture. Whether can I produce this string? Can I produce this string with the help of the context-free grammar that already present inside the compiler? It's trying to produce it. If it is possible to produce by the context-free grammar, then it has no syntax error. In case if it is not, then it will generate an error with a possible error in this code. And once the syntax analysis does, the semantic analysis comes into picture. It goes one step ahead and checks, is that y type and x type are matching. If it is not if they are not matching, then we'll look for is there any implicit conversion possible? If not, it will produce an error. Okay, so these are the various levels of analysis of the code with the help of various phases of the compiler. Okay, so this has no syntax error, so I'm not including here. Okay, as I told, there are three main types of errors: lexical errors and syntax errors, and then semantic errors. Mainly what we call here, from here to here, simply we call compilation errors. In the exam, mostly they will mention they are compilation errors. They may or may not ask whether it is lexical or syntax or semantic. As you know, most of the programmers, they don't worry about which kind of error, but is it compiler or not. Okay, sometimes you don't see lexical error, but you will see syntax semantic. Sometimes you don't see lexical syntax, but you may see semantic. Doesn't matter, what level you see an error, but it is a compilation error. Okay, so what are the lexical errors that you may see? Sometimes we write, I told 1 2 AB. This is gonna be an error because this group is invalid sequence, right? It's an invalid character sequence. It's invalid token. Right. Sometimes you may see something like you have started with single quote and you have written A, you forgot end it. Then this is going to mismatch the character constant pattern, because character constant will have the two single quotes, within that you will have a character. So it's going to mention that the end character pattern is missing. So it's also going to produce the lexical error. Okay, that's about a lexical analysis. It's only look at the group of characters, will it have a meaning or not. Okay, it might, the characters group may be divided into multiple tokens, but do you have a meaning or not? Do you have a valid token to produce or not? Syntax errors. What are the possible syntax errors? I have just informed. Suppose you have x is equal to y, a semicolon is missing, or sometimes you have written int and you, for instead of variable, you are writing 100 here, semicolon. Then how that 100 can come here as a constant, right? The 100 here, it's expecting identifier, but you are giving some constant. The compiler understand with the help of the grammar. And similarly, you may see various errors in syntax analysis. Semantic errors, if you have something, char, you need to analyze the code properly with the help of types mainly. Let's say you have char x, and some compilers do conversions, but I'm only talking about, let's say x is equal to, you have some character, y is equal to, okay, I don't want x value, let me take directly y value. Y is equal to 1 2 3 4 5, something like that, and you are trying to assign that y into x, then definitely y is 2 or 4 bytes. Now you are trying to convert into 1 byte. The compiler may produce an error. Some compilers will deal by doing truncating that 2 bytes into 1 byte. That is okay, but there is a possibility of a semantic error as the types mismatching here, y and x. If you really want to convert 2 or 4 bytes into 1 byte, then you should do explicit type conversion, like x is equal to the what type you want to convert. The y is actually 2 or 4 bytes. I want to convert into 1 byte. You must mention that size. That size is your char. The char is going to be the typecaster here. This char, that means y will be converted into 1 byte now instead of the taking as 2 or 4 bytes. Here there was no typecasting, that's why compiler may produce an error, but here the compiler will not produce an error. So this line you try to replace with this one, this code will be properly executed without any issue. But if you do this, you are expecting y to move into x, but you don't understand the value of x, as you are expecting the y should be moved to x. But here you are explicitly saying that I just want 1 byte of the y. So it's very easy to understand. The compiler as well as the code is very clean. but this line is going to, this program is going to produce error at this place, the semantic error, the type mismatch is happening here. Okay, the L value, R value types are not same. Fine. So these are the various errors we have in compiler, in lexical, syntax and semantic. Fine. Which of the following codes they are producing some syntax errors? Which of them? The first one, the FRO, fro, that can act as a function name, right? FRO is not a keyword, so it's identifier, so it looks like some function followed by void arguments. There are no arguments inside, so there is no syntax error here. It's absolutely correct, but you want syntax error. Which one is producing syntax error? The next one, for, is a keyword. You know that for used for the loop, and now the for expecting, there are 3 expressions in the parenthesis, but you did not mention any expression. It's going to give you syntax error, so it produces syntax error. Syntax error, right? When will not produce? If you write something like for, at least some values, expressions like a semicolon, b semicolon, c, something like this, then you don't have an error. This is absolutely no syntax error at this point. You may have semantic error if a, b, c are not declared, but there is no syntax error when you have a semicolon, b semicolon, c, or you may write any other expression in place of a, b, c if you want it. Okay, this is correct code syntax syntactically. What about the next one? Fro, again function name. Here 2 parameters, here no parameter. This is also having no syntax error, and this B is going to have the syntax error. And the for is a keyword, fro is not a keyword. So fro treated as identifier, but for is not identifier. For is specified for the loops. That keyword has some reserved meaning inside the compiler. So it knows whenever for appears what syntax it is going to look at. Whenever if else comes or switch comes and do while comes, the syntax is very clear to the compiler, because these statements are already predefined while you build the compiler, right? Which of the following again produces a syntax error? Which of the following codes are producing syntax error? Now you can see the first one, x is equal to y semicolon, id is equal to id semicolon. No syntax error at all. X plus y semicolon, again no syntax error. Do not expect that it will assign to some LHS or L value. Here not required. It's an expression, right? Any expression you can write without assigning to somebody. Like you can write 2 semicolon or a semicolon, a plus b semicolon. The compiler understands the code. This maybe you can optimize further. You can delete this line, because it's not going to impact or change any variable value or any data. So you can ignore that while we can delete that while doing code optimization. But right now these two are having no syntax error. And the third one, x space y semicolon, and this one is actually looks like an error, but it could be possible it's also possible no syntax error. Why? If x is some type, you can see that in some codes like type def, you have, let's say you have int here, in place of int you want to write x, and that x is going to specify now int. So it understand what I'm trying to say here. The x can act as an int, and it's another name for int. So int y is actually the right syntax, right? So if you look at it, the syntax analysis is not going to check what is this x integer or not, but it knows that okay, x space y semicolon, it's a valid syntax as per the syntax analysis, whether x is int or not, right? Because it is valid statement, it has no syntax error, but it may contain compilation error but not syntax error. So this is not having syntax error, okay? But when you are not aware of type def statement, definitely you think, even I thought earlier in the beginning it was syntax error, but because of this statement, this line is ignored by the compiler in syntax analysis. because there is no connection between these two. Semantic analysis will get a connection. In case if you don't have this line, then this will generate an error. This will generate an error because it's going to map in semantic analysis. If you don't have this line, this will generate semantic error. If you have this line, semantically all the types are properly defined. You are declaring the y as an integer, it's correct. So understand why this x space y semicolon is having valid syntax. But last one, x space y, has no meaning at all. You are missing some operator in between, or at the end semicolon required if you want to say it's a declaration. But anyhow, I can't say what's this statement, so this will generate an error. Which error? Syntax error. The other statements may produce error, but they don't produce syntax error. They may produce compilation error if you don't handle this x and y properly. Okay. But 3, you write in any program anywhere, they will never have the syntax error. They will never have no syntax error in this. You may have a compilation error, but not the syntax error. Maybe due to semantic analysis, these statements might give you the error. Which of the following again produces the syntax error? Can you identify now? We did already a few examples. Pause the video and try to understand what error could be possible from these options. Okay, the first one, f, I told you that it's a function call. That's okay, it's a proper, no syntax error. 1, 2, 3 followed by parenthesis. What is that meaning, right? If you are writing an expression, do you have any meaning to that? No, right? This definitely produces. You can't say it's a function call, you can't say expression, because 1, 2, 3 followed by parenthesis has no meaning at all, right? And it definitely produces a syntax error. Okay, C, yes, a valid expression. You can mention operand within the parenthesis, no syntax error. And the last one, 1 plus 2 parenthesis, it is also valid expression. Okay, so the option B is only the syntax error. Fine. In context free grammar, we have the first topic is derivation of a string. What is the derivation of a string? It's nothing but how will you derive a string if I give you a context free grammar? Because context free grammar is going to represent a context free language. It's nothing but syntaxes only. So that language has a lot of syntaxes. Like if you take the C program, all the programs, every program that you write, it has the valid syntax. Similarly, when you write a context free grammar, it's going to produces the valid syntaxes, nothing but valid strings. And now the first thing is, how do you derive a syntax? Nothing but how do you derive a string? There are 3 ways. Like the first one, you have leftmost derivation technique. Leftmost derivation. Also you may call it as LMD. The second one is rightmost derivation. You may call it as RMD, rightmost derivation. And the third one is a parse tree, which is called as a derivation tree. Now the first 2 are called as, they are going to be linear form, you write in sequentially, so they are linear derivations. And the third one, you draw a graph, it's a pictorial representation, so it's a non-linear representation. So linear derivations, non-linear derivations. In the linear you have 2 types, non-linear you have the parse tree. Okay, let's start with a leftmost derivation. Okay, you have leftmost and rightmost parse tree. Let's look at all of them together. Let me take one example. The context free grammar, I'm just taking one example. S derives A, B, comma, A derives, let's take A, capital B and B derives, let's say, D. You have something here. This is my grammar. It has three productions. S has one, A has one, B has one. Now, what string it's deriving? Maybe one or more, or zero or more, you can say sometimes. But this one especially deriving only one string, where S depends on capital A. Capital A gives A, D, where B, when you replace B with D, and B replaced with D. So I have the only one string that I can generate with this grammar is A, D, D. That's it. You cannot generate any other string. It need not be one string in general. It could be zero or more strings from any context-free grammar that you take. But if it is having more strings, you should be very careful. Is that one way or more ways to derive a string? You have leftmost derivation and rightmost derivation you have. Rightmost derivation and parse tree. Okay, what is the leftmost derivation? See, when you look at all of them, everybody will start with the same concept, right? You know, they start with S only. Everybody will start with the start symbol of the grammar. But how you do it? So now you have, here we'll complete the LMD, then we'll go for RMD. S has only one production, no doubt you have to substitute with that. But when you have more than one production, you should choose carefully which production will derive the string. If it is not deriving, there is no use of writing all the steps. So you need to consider carefully that you should choose the production carefully that should derive the string. But always you should know, if more than one non-terminal in the same step, you should use the technique, which technique you are following. Okay, in leftmost derivation, we call every step here, every step we call it as sentential form. So when you have the sentential form, like AB is a sentential form that is derived with the help of the start symbol. Now out of these two non-terminals, and ignore the terminals because terminals you can't substitute further. Now if you have more non-terminals, then which one to substitute first? If you are following LMD, leftmost non-terminal will be substituted. If you are following RMD, rightmost non-terminal is substituted. If you are following parse tree, you will draw a graph, we will see that soon. Now here, the first you have substituted S, then now you are substituting A. Why? Because A is the leftmost non-terminal. A is the leftmost non-terminal. So what A has? A has AB production, small a, capital B. Now which one you will substitute? There are two B's here, but the leftmost non-terminal, that's it. What will you substitute with the B? B is having only one production, that is D. So you are going to substitute with D. And you may ask, sir, why can't I substitute the two B's with the two D's? No, at a time you will substitute only with only one non-terminal. So you should remember that, because you need to calculate sometimes how many steps are taken to derive the string. Then you can't do multiple substitutions in the same step. Okay. Finally you have only one non-terminal, so substitute that. That's A, D, D. You got your string, right? And in this process, in this derivation process, in each step you have substituted leftmost non-terminal. You have substituted leftmost non-terminal. So that's called as a leftmost derivation. If you want to derive a string, you need to start with a start symbol, and in the process of deriving a string, in every sentential form you will always substitute the leftmost non-terminal. So that's called as leftmost derivation. If you understood it, and tell me how many steps you have taken, and just look at the number of edges that will be considered as steps here. Very simple technique. So let's start with number of edges. 1, 2, 3, 4 edges. It means you have taken 4 steps. Okay, you have taken 4 steps to derive this string. And here you can say 4 substitution, 1, 2, 3, 4. So number of substitutions, nothing but number of steps. Okay, number of derivative steps. Now this as we will again substitute with its production AB, but here which one you will substitute? Who is the rightmost? Here it's only one, so that's the rightmost, but in this step B is the rightmost. Okay, whereas in LMD A is the leftmost. Here we take rightmost. Rightmost non-terminal will be substituted. So what do you substitute? Only D is there. D you will substitute. At this point only A is there as a non-terminal, that is only the rightmost you have to take. That's going to be A, B, D. At this time only B is there, so that is your rightmost. Fine. In each sentential form or in each step, the rightmost non-terminal is substituted first, is called as rightmost derivation. And finally the parse tree. While you are constructing the parse tree, either look at LMD or RMD enough, because both will give you the same parse tree if you really have only one way to derive. Here S is going to be substituted with AB, so we will construct a production tree. Every production has a production tree. This is actually a production tree. Now the capital A is having AB, so there is another production tree will substitute. So we are going to concatenate so many production trees to get a parse tree. Now another production will have a corresponding production tree. This A will have small a, capital B. So every non-terminal I am putting a circle just to understand, but circles are optional if you don't want. And capital B you have a D, and this capital B has a D, and all the leaf nodes you just collect from left to right, you will get a string A, D, D. You will get the string, required string. All the leaf nodes you collect from left to right, you will get a string. Now this is these are the three techniques, or you can say derivation approaches to derive a string. And now in the exam you will see how to find the number of parse trees or find the number of derivations. When you see that question, you may see more than one derivation for the string. In that case, don't follow all the three, just follow any one, because if I have 3 parse trees, then you will definitely have 3 RMDs, you will have 3 LMDs. If I have only one parse tree, then you will have only one LMD, one RMD, you will have one LMD. So this is how you need to approach. The best technique is always use the parse tree. If you really get one parse tree, that means you will have only one derivation, right? That derivation you can follow any of these 3. Is that clear? Don't say I have 3 derivations. We have 3 types of derivations, but not 3 derivations. We have only one derivation to derive, but we have 3 types to derive. That to represent, we have 3 types. Fine. So number of derivations for this string using this grammar is only 1. That is one way to derive. That's it. So if I have a 1 parse tree, means I have 1 derivation only. Clear this point? Okay. Now we have the 2 types of grammars. I have taken an example to understand, but let me explain first what is ambiguous and unambiguous context-free grammar. It's basically depends on how many derivations are there for the strings generated by the grammar. In general, you think about if there is a string generated by the grammar, how many parse trees possible? Right, 1 or more, right? If that is possible to derive, 1 or more. If not possible, 0. Okay. Now let's say if the grammar is ambiguous. Let me write the definitions first. What is ambiguous grammar? What is ambiguous grammar? unambiguous grammar. If the grammar is ambiguous, ambiguous means definitely there is some kind of confusion while deriving a string. You don't have a clarity because you will have multiple parse trees. It means it need not be for every string. You find some string, at least one string in the grammar that has more than one parse tree. It means the grammar is ambiguous. When you say unambiguous, every string that is possible to generate from the grammar should have exactly one parse tree. That means exactly one derivation. Okay, so I'll just write in a simple concept or simple way to represent. There exists means some string which is belongs to a language generated by the grammar, right? But that some string is, let's say, W. That W belongs to the language generated by the grammar, and this W has more than one parse tree. More than one parse tree. Then we say that G is called as ambiguous CFG. G is called as ambiguous CFG. When we say if there is some string which is generated by the grammar and that has more than one parse tree, it means you have multiple parse trees to derive the same string. For that, program is not recommended, so you need to convert into unambiguous to have a clarity. Anyhow, what is unambiguous CFG? Let's say G is unambiguous CFG. Here we should say every string, not one string or two strings, every string that is generated by the grammar, has, the W has exactly one parse tree. You don't have multiple parse trees. Then we say the G is unambiguous context-free grammar. So now every string has exactly one parse tree, unambiguous. There is some string which has more than one parse tree, which is ambiguous. Okay, unambiguous, everybody will have one parse tree who is generated by the grammar. Who is not generated by the grammar, we don't expect. Remember that. Only the strings which are generated by the grammar, we are giving the condition. Okay. Now let's find out this grammar is ambiguous or unambiguous. Just check. Is this grammar ambiguous or unambiguous? Okay. Think about the possible strings you can generate from here. If I'm thinking here, the first string, you just look at the first string. I'll just write A is possible. Like always you start with S, right? S can generate A. What is the other possibility? In the open parenthesis, open and closed parenthesis, within the parenthesis, L can give S, S can give A back. So there is one more here like A. And what else? Is there any other string that you can generate? Let's try that. S, you always have either A or this one. So when you have this one, there is a possibility of L in different ways. One time you have taken S, one time you have taken S, other time you take this one, LS. When I take here LS, yes, already you can have A. That L, you can have either S or LS. Right? I'm saying S, you can take A, and this L, either you can take S or LS again. So if you take S, you will have one more A here. Similarly, you can write a lot of strings here. The problem with this kind of grammars, how long you do that? Is there any algorithm to check them? No algorithm. So you need to verify for every string. If you really get a string which has more than one parse tree, you're so lucky because you can say it is ambiguous. But if you don't get, how long you are going to check? How many strings you are going to verify? It's going to consume a lot of time, and you may not end, right? You may not end to check. So that's why this problem actually checking ambiguity is undecidable. Means we don't have generalized algorithm to check this grammar is ambiguous or unambiguous. But easy examples you can do it. If really the grammar example looks difficult, you may spend a lot of time. You may conclude sometimes wrong answer too. Okay, anyhow, so let's check for these three. And in case if you get later on this if later on if you find some string which has more than one parse tree, mention in the comment. But I'm just helping you how you should proceed to check the ambiguity. First you go for A. How many ways you can produce A here? Only one way, S2, this one. How many ways you can produce this one? There's only one way. You go here and L you put S. That's it. How many ways you can generate this one? Only one way. You go here, L you substitute with LS, and that LS you have to put AA. So every time you are able to get only one way, so you can conclude this grammar is unambiguous. Only with these three strings I am concluding, but I may be wrong. But in the exam, most of the time 3 or 4 strings, the first 3-4 strings, you will be having an answer. If you don't have it, then you should spend more time. So give 1 or 2 minutes more to check, 3 strings more, total 5 strings you check for this grammar, then conclude the right answer. Because you need to answer in 3 minutes. Even there is no algorithm, then you need to understand or analyze in your approach. Or that approach is start with the first string and go to the 4 or 5 strings and verify other 2 strings, next 2 strings, then conclude it. But if you are able to understand the grammar, you are able to get unique way to generate the string everyone, like this string has 1 parse tree, this one has 1, this one has 1, then you can conclude this unambiguous. Okay, so take it as homework, but I just concluded by looking at these 3 strings. I may be wrong, but you just conclude after verifying 3 more strings, just conclude if really it is grammar is unambiguous, and it is unambiguous. Okay, so this is how you approach it. As we don't have algorithm, so best way to solve in the exam is take the first 4 or 3 to 5 strings. If the answer came in the first few strings only, then your job is over. How do the answer come? If anybody has more than 1 parse tree, then ambiguous comes out. When the ambiguous comes out, don't worry about other examples, like you need to take other strings. Okay, now let me take another example to explain. Now you can see here you have the string. Definitely this capital A is going to generate something which is either B or A repeatedly followed by B. So overall it's just like A star B. The language generated by capital A is like A star B. So when you put there A star B followed by A star B, something like that here. I'm just mentioning what's happening here, but really you don't need to worry about it. It's going to repeat that A star B. So either B will generate or A star B, and when you put here, you will be having the language like A star B dot A star B. Now you give me any string from this. Do you have only one way? Suppose I give the minimum string double B. How many ways you do? Directly you go to capital A B and another capital A B. Only one way you do it, like S A, then A derives B, other A derives B. That's it. And if I ask another string from this, that is A B, let's say B, A B B. How many ways you do it? The first A B you have to do from the capital A, other B you have to do from the another capital A. So because of these 2 B's, the A present before the first B or A present within the 2 B's, you can easily understand how to generate it. So it's also unique way that S A, and this A has to generate A capital A and A B and this B. Similarly, you take any string, it looks like you get only 1 parse tree. That's how you understand, but I told you there is no other way except understand what strings you can generate from here and put them in the lexicographical order one by one and look at, observe 4 to 5 strings possibly, then conclude it. When you keep on practicing more, after 1 or 2 strings only you will understand, okay, the strings can come uniquely from this side and that side, you will understand easily. Okay, so it is also unambiguous. I'm concluding very quickly, but you should conclude after few strings. Okay, I have already given approach. Just what you do is, you already know the language, right? A star B, A star B. From this, try to put all the strings. When the grammar is so big, don't worry about the language. Language you may not get it sometimes, but get the strings possibly. The next string maybe you try like a B A B. Next string you try A B A B. Next string you may try A B B, something like that. Okay, then you will get to know, okay, only 1 parse tree any string that you take from here. Okay, yeah, Now, how do you answer in the exam? Are you going to try like that all the time? No. Mostly what do they ask in the exam is about ambiguity. They don't worry about unambiguity. The reason is unambiguous grammar may waste your time. Even you spend 3 hours, you may not conclude the answer. So are you going to spend 3 hours in the exam? No, right? So mostly they will predict, or mostly they will give you. They are predicting that you should, approach the ambiguity concept. You need to guess when the ambiguity comes, what kind of the productions might present in the grammar. If you look at this one, just by looking at it, I can say it's ambiguous. You may ask, sir, how did you conclude without practicing or without verifying the strings? That's what I'm talking about. There are some principles, or there are some shortcuts to understand ambiguity. Here, if you look at how many non-terminals are there? Yes, only one. When that non-terminal, it could be any non-terminal, but a particular non-terminal I am talking about. In the grammar, S is a non-terminal that is having both left and right recursion. If you see that, this S is actually having right recursion here and left recursion. So if you look at S derives AS, what is this called as? Right recursion. And what is this called as? Left recursion. Why? Because the first position of the production, you have the same symbol as LHS. This is direct, but sometimes you don't see S here. You may see some other non-terminal, but that will give an S. That's fine. So here, when we say left or right recursion, here something is there, you don't care, either directly or indirectly. But here in this production, somehow you get in the last position S, you get either directly or indirectly, we don't care. And here the first position you got S, then we say S is participating in left recursion. Okay, if it is direct, you will see in the production itself. If it is indirect, after substitution you will see them. Okay, and now tell me, is the same non-terminal participating in both left and right? It means you have to prove that I have a left recursion and right recursion with the same non-terminal, either directly or indirectly. So here directly is there, but not required. Now here S is having right recursion as well as left recursion. So you can say directly it is ambiguous. If you really wanted to check that, then how much time it take? It's going to take much time. Let me help you how much time it takes. See, first you will try to understand epsilon. How many parse trees? Only one parse tree. And now let's try another one, A. Then here you may get the answer quickly, but some grammars you may not. Here S derives AS, this S is epsilon, and you got one more. What is another more? Another one, that is S A, and this one is epsilon. So lucky. But if this is not an epsilon, the string length could increase a little bit. 2 length might give. Right now 1 length is giving, so you are so lucky. So fine, you got ambiguity. We will take some more examples to understand here. Then why we don't approach this? Because while we are doing it, if the length increases, then you need to spend much time here. You need to spend much time to get the string. But if you are already having the property, directly you don't need to verify even 1 string or 2 strings here, 3 strings or 4 strings. Directly you can see, okay, S is participating in both left and right. Forget about other non-terminals. Other non-terminals may not have recursion, it's fine, but S is having both left and right. Then the grammar is ambiguous. Remember, the grammar should generate some string. If epsilon is not there, somebody is given AS or SA, and it's not the valid, right? So we don't talk about the grammars which is not giving the strings. Okay, always talk about the simplified and good grammars. Okay, at least they should generate some string. Null productions you may keep, it's fine, but don't keep useless productions. Okay, another good example. Now previously the left and right recursion were present in different productions. That's fine, whether they are in the same production or different productions, it's okay. But is that S participating in both left and right? See that in the same production you have the left, of course same production you have right. That's okay. SS will give you both left and right recursion. Is that clear? So due to that, it will definitely give more than one parse tree for some string. Okay, there are strings which will have more than one parse tree. It is also, you can see S is having left recursion as well as right recursion. So it is also ambiguous. And if you try to do that, okay, I'll just talk about this example, S as A. This would be sufficient to understand. Even you can ignore this because that's not going to give any unambiguous concept because of only that. Anyhow, this is already producing ambiguity. So I'll just take some simple example for this, how you do verifying the ambiguity. First you try on A, only one parse tree. Try it, you will get it. Double A, one parse tree only, you'll get only one. Because S you have to put A, S you have to put A only one way. When you have 3 A's, you may have more than one parse tree. Let's see. S, SS. Now, how do you get the 2 A's? There are two ways. Either you get 2 A's from here, or you can get 2 A's from here. Simple. Total 3 A's you need to produce. 1 A if I put here, 2 A's you have to get here. Or if I get 2 A's here, you should get 1 A. So you decide how do you want. There are two ways to do that. How to get 2 A's this side? Put 2 A's. Then A, A, A. And here if I put 1 A, you have to put 2 A's here. Then you have 1 A, 1 A. So now you see there are two parse trees for this. Then stop here. Don't verify for any other string because you got ambiguity. So if you have this concept, really do you need to verify the strings? Not at all. Right? In the exam, that's going to be shortcut for you. But observe directly or indirectly. Sometimes it could happen like, S derives, you will see A here, but you are able to see here something directly, and let's say C, but here A might be giving you something like a left recursion. See that S is participating in the right recursion, but looks like there is no left, but there. Capital A, when you put with SAB here, S comes first. That means here indirect left recursion is there. That means S is participating left and right. A may or may not participating, we don't care. But S already participating in both left and right. So this grammar will have ambiguity, will have a string which will generated by the more than one parse tree. So this is another example where it is also going to be ambiguous context free grammar. This is also ambiguous. Okay, this is also another example I have taken. It is also ambiguous. The actual example I have here given here, that is ambiguous too. Okay, the three examples I have taken to understand the ambiguity. Okay, now you don't need anything to prove. Simply you see it, you will say it is ambiguous. Yes or no? How did you say that? See, E, left and right recursion with E. Other production it's fine, but still you can just conclude with this production, and it is the valid productions because you can generate some strings from this grammar. Fine. So it is ambiguous. All the productions are useful. Okay, now it's one question or few questions we have to understand the grammar. You have three options here. Fourth is none of this anyhow. Just check is it ambiguous or not, and left recursion is there or not. Okay, just take 20 to 30 seconds or 40 seconds, answer it. Ambiguity is there or not? Really difficult question. So how do you do that? You need to start. See, there is no such left and right recursion. If you don't have both left and right recursion, then you can't conclude anything. If you have it, it is ambiguous. Same non-terminal participating in both left and right recursion, you can conclude. But if you don't have left and right recursion with the same non-terminal, you don't know. It may be ambiguous, may not be ambiguous. So you should be very careful. Example, see this S derives AB, or I can say simple, very simple one. S derives A or A derives A. You see that there is no left recursion, there is no right recursion, still there is ambiguity. Okay, ambiguity possible because of many reasons. One reason is due to left and right recursion participation by the same non-terminal. Other reason, see that You don't need any recursion to produce more parse trees for the same string. Okay, so you should be very careful. Don't assume only one reason. There are multiple reasons to have ambiguity. So this may or may not have the ambiguous. Now let's check. The first string you may have AB, right? That's a possible, right? How many ways? Only one way. Another one string you may you have to go there, AASB. In case if you have seen lot of examples, this grammar I can simply write other way. See that anyhow capital A is having only one job, right? One job means one production. Then why are you maintaining two? It takes much time to derive a string. So you have a shortcut. So directly you put there. Now see how many parse trees are there for every string. The grammar is simple. That's it's generating equal number of A's and B's when A is followed by B's. But other than epsilon it will generate. Okay, AB only one parse tree, and A square B square, that is double A double B. It's also one parse tree. Go there and put AB here. That's it. Next one A cube B cube. So everybody will have only one parse tree. You keep on substituting. Here it takes less number of steps, but here it will take more steps. Just to save my time, A has only one job, so I just substituted that. In place of capital A, just I put SB, but it will not going to change the type of grammar, ambiguous and unambiguous. It will keep same, because A, instead of taking one step, I'll just put there. So I am saving one step, that's it. Now this grammar is unambiguous. Unambiguous. And not only this grammar, this is another grammar, but which is equivalent to the same grammar, just with the help of one substitution, that's it. It is also unambiguous. That's why practicing many grammars will give some kind of insight without without verifying the strings. You can conclude what's actually happening in the grammars. So now you got the answer, unambiguous. Do you have any left recursion? Yes, S is not a left recursion. S, if you get a capital A there left side, then it is a left recursion. You put there, in place of S, if you put small a capital A, but capital A is coming in the middle, right? Not in the first place. So there is no left recursion with A. Is there any left recursion with S? Oh, here small a, here small a, no left recursion. So this is not going to happen. Okay. So it is unambiguous grammar. Next topic is a left recursion elimination. What is left recursion elimination? Like a top-down parser may have a problem if you use the left recursive grammar. That is why we require to eliminate. We are going to eliminate the left recursion. So what kind of problem it faces? Top-down parser follows leftmost derivation. Due to that, if the first place is having left recursion, it keep on substituting, and there is a possibility it may never stop. So that means it might enter into infinite loop. This might be a problem for the compiler. That is the reason we eliminate left recursion elimination. What is the left recursion? In case if you have something like this, X arrow, let's say X A or B. It's a direct left recursion called as. Sometimes indirect left recursion, like X derives, you have Y followed by some alpha or beta, and the Y you might have X some gamma or something like that. Okay. See, the Y, when you substitute with X gamma, the X going to come in place of Y, X gamma going to come in place of 5, the X will be in the first position. So this kind of grammar will have the indirect left recursion. Even Y also having here left recursion. When you substitute X with Y alpha, you also get a Y in the first position, right? And this is called as direct left recursion. Okay, it might be direct left recursion or indirect. Any kind of left recursion we should eliminate. But before that, we'll try to understand how to eliminate the direct left recursion. Then we'll go for how to eliminate any left recursion, whether it is direct or indirect. If you want to eliminate the direct one, we have very simple concept. Like you have x derives, let's say xa or b. Then to eliminate it, very simple, the x, this b we write first, and then we are going to introduce new non-terminal, and that x dash is going to convert this as a right recursion, a x dash, because we have taken new non-terminal to repeat this a, okay, or to end this you need epsilon. That's all you require to write. So I'm going to generalize it, but how do we write? In the first production we will take the non-recursive term. In this xa repetition, that a is going to repeat, that a we are going to repeat with the help of right recursion. That's it. Previously left recursion, now it is right recursion. So elimination of left recursion, nothing but converting left recursion into right recursion. Now in general, what is the formula we have? In general, suppose you have a non-terminal a that has a lot of left recursions, let's say direct left recursions only, like you have n left recursive terms productions, and then let's say beta 1 beta 2 is not having any left recursion, let's say k non left recursive terms. Then how do we convert this grammar into right recursive grammar, that is without left recursion? I told you these non-left recursive terms we are going to write first because they are going to be the reason to end this a's. So this first position we are putting beta 1. So we are going to take the help of beta 1 a dash. This a dash will repeat alpha 1 or repeat alpha 2 and so on. And for beta 2 we may have the a dash and so on. How many this non-left recursive terms? This many. If you observe carefully, that a is going to end with beta 1 beta 2, that we are taking first, that's it. That alpha 1 we will take with the help of a dash. What a dash does is going to repeat this alpha 1 alpha 2 alpha and so on, like that. Alpha 1 a dash with the right recursion concept, alpha 2 a dash and so on, alpha and a dash. To end this you need epsilon. If you don't want epsilon, use the elimination of null production concept, so that you will get additional productions here and there. Okay, so this is the CFG without having any left recursion. So we are converting left to right when you have a direct left recursion. Let's see some of the examples to do it. Okay, one example already I have taken, but I will take again. Let's write x derives xab or xcd, that's it, or def, let's say. Now how do you eliminate? X derives, who is the non-left recursive term? Def. So we'll write first def, and then you require some new non-terminal to repeat this ab and c recursively. So the x dash is going to repeat that ab with the help of right recursion, or c with the help of right recursion whenever you want to stop, because if you don't write this epsilon, you see that the x dash is there everywhere, and if you don't write anything here, impossible to derive any string. So it's very important, x dash is null here. That means when you put epsilon you will get def. See that x can derive def. Clear? So this is going to be non-left recursive grammar. So we have a left recursion, we don't have a left recursion. Right. If you don't want epsilon, you need to do one small thing. What is that? Just eliminate this epsilon. How do you eliminate? X derives def x dash, and write our entire grammar as it is except epsilon. Except epsilon. Now what you do when you eliminate this epsilon, that means x dash to epsilon you are eliminating. So wherever x dash is there, put epsilon there. If you put epsilon here, you get a def. So you need to add extra production here. That's it. If you put epsilon here, ab you get add here itself. I am adding here itself, ab. If you put epsilon here, you get a c. And this is also right grammar without a left recursion. So either you can write this one or this one. This is a with null production, this is a without null production, but both are not having a left recursion. So this is the first example. Let me take second example, which will be concluding the direct left recursion. Suppose I have x derives x a or x b c or d x e or f g or h. Now how many left recursive terms? I'm not asking how many recursive terms. There are so many recursive terms, but how many left recursive? Only these two. So these three do not have any left recursion. Do not have any left recursion. That's x derives. Now we are going to take care of this 3 to end this recursion. That's dxe. We require new non-terminal x dash. Fg. We require new non-terminal hx dash. So all the non-left recursive terms we have substituted at this place. Okay. Oh, sorry, these two places. These two places. It means we get these 3 possibilities only. And what x dash does, either it repeat a or bc. So x dash repeats a using right recursion concept. You see right recursion, but this is x derives xa, this is x prime derives a x prime, or this one bc x dash, or epsilon to end that. That's it. Fine. So eliminating direct left recursion is not the big deal. It's very easy. In the exam, mostly you will see direct left recursion. So you can directly eliminate it, and you can see the options which are going to look like this one or without epsilon. So when you don't want epsilon, put epsilon everywhere where you have the x dash, so that here 3 additional productions comes, here 2 additional rules will come. Fine, that's it. Now if you want to eliminate indirect left recursion, so this approach will be useful, but you can't apply for every non-terminal as it is. Every non-terminal you can't apply as it is. So there should be a mechanism to eliminate indirect left recursion. What is that mechanism? Okay, what is that mechanism? The mechanism is very simple. If you have many non-terminals, see that I'm going to have many non-terminals here. So what strategy we are going to apply here? Okay, let me write this way. Okay, that's it. Now you see, I have 2 non-terminals. I have 2 non-terminals S and E. S and E. So which one you are going to eliminate first? You decide. So I'll follow always from top to bottom. Okay. S, I will try to ensure there is no left recursion. Then capital A, there is no left recursion. I will follow particular order. But while following, very simple technique is, the first non-terminal that you take, S productions, only apply the direct left recursion elimination. Then why don't we apply indirect? See, here you have a capital A, here also S may come. Don't need to take care of that in S. A can also take care of that. So when A is depending on S, you try to terminate that. You try to stop that left recursion. Okay, convert into right recursion if possible. So while doing from top to bottom, the first step, the first non-terminal that you take, no worry about indirect. But when you are taking A, the already S was eliminated from direct, so that S you can substitute here. That S you can substitute. If you have other rules like B, in B you need to take care of A and S. Both you need to substitute in B. But that should be only when you see in the first position. And after that, if you see any capital A, don't substitute there. Only we try to substitute in the first position, like this first position only. Okay, let me apply the technique. The technique is S, A, B, doesn't matter how many non-terminals. First, you apply here direct left recursion elimination. In A, what you do, you may have indirect. So what we do here, this first we will apply substitution technique, substitute S, then apply, if required, direct elimination, direct left recursive elimination. B, what we do, you need to substitute S as well as A within this B, then you apply After this you apply direct elimination, direct left recursive elimination. In C, what you do, you need to substitute S if required, A required, B required, but they might be substituted more than once. When you substitute S, you may get A. When you substitute A, you may get a B. So it could be possible that there are many recursive substitutions. At the end, you apply direct left recursive elimination. Okay. Then when you have D productions, S productions, A productions, B, C, D, you are applying step by step. So if there are many non-terminals in the grammar, you need to follow a particular order. You decide. No need to start with S, but in general we will just follow from top to bottom. Okay, like S productions first given, A production next, B production next, C, D. If that is a given order, just follow it. But no need to be in the same order that we take. You can follow in reverse order, you can follow from anyone, but you should remember S is a start symbol. Okay, here what we do, substitute S, A, B, C, then you apply direct left recursive elimination at D. After substituting all this, and where do you substitute? Only at first position of the production. In case if you see something like this, B arrow A, S, A, D. If it at this point of time I told you to substitute S and A, but don't substitute here, because small a never gives you left recursion. When you already know there is no left recursion here, don't substitute. Substitute only when you have directly S here. Then there is a possibility of getting a capital B here, right? So only at first position you will try to substitute. And also ensure the given grammar is not having any useless productions or null productions or unit productions. Take the simplified grammar always. You may produce the grammar which is having null productions, but take the grammar which is simplified so that you will not have many substitutions. Okay, that's the technique you are going to follow. Now this technique I am going to apply here. Okay, this is a technique. Okay, here especially. Now tell me which one you want to follow. I will follow the same order. Okay, the first step is step 1. S derives as A, B or A, B, C or D, E. Now tell me what I have to do. I will only apply direct left recursion. Don't look at any indirect left recursion, because that we don't worry here. Right? S and A might be participating in recursion, will terminate from A. We don't terminate from S. Okay, we'll keep S, we'll keep A within S, but will not keep S within A. So that somehow left recursion will be eliminated. What we assume, these two are non-left recursive terms. Even though indirect is there, but we don't care. So here we directly apply the rule. You know that rule. A, B, C, S dash, D, E, S dash, and what S dash does is A, B, S dash or epsilon. So this is the final answer for S. This is the final answer. Now I am going to use this S productions in future whenever I want to substitute here, like this A, B, C, D productions. Now we have only A productions there. Do you require to substitute? You can see that. Do you require to substitute? Okay, I'm just deleting this. That's just the technique we are following. Now here we have the A production. That's a step 2. Step 2. What is it? A productions, nothing but here A derives AB or SA. Now there is a requirement of substitution. Why we need to substitute here? Because S might produce indirectly capital A. Even though A was producing indirectly capital S, we didn't do the substitution, as it is a step 1. We don't care, because previously there was no elimination of the left recursion. So this is the first one. The first step always we take direct left recursion elimination, but second step onwards will take care which were eliminated in the previous steps. In the previous steps S was freed, that's why only we substitute S. We don't substitute, like if any other non-terminal is there that you are doing in step 3 and 4, that we don't do it. Okay, so here we substitute S. What is S production? I'm going to substitute here S. Substitute S. What are the S productions we have? The final productions only we substitute. S has two productions. I'll put here. So what is the result you get? A derives AB, and this productions only you substitute, not this productions. We always substitute which are there in the final answer. Okay, A, B, C, S, A, B, C, S dash, and also A is there here. That's one production. Another one D, E, S dash, D, E, S dash, and followed by A. We have substituted it. Now see, do you have any more S in the first position? This small a, capital A, D. No, right? Because sometimes you may see some other non-terminals while substituting this. Here in step 2 we will only substitute S. In step 3 we will only substitute step 2 and step 1 non-terminals. Here S is chosen, here A is chosen. In future these two will be substituted in future steps. Okay, but at this step is the final step, as we don't have any other non-terminal. Fine, now we got the substitution. Then if you don't see any capital A in the first position, no need to eliminate. Elimination required when you have the recursion, right? Here direct left recursion is there, that's why we are eliminating. So these two are non-left recursive terms. We will write here A, this is like a beta 1, this is like a beta 2, A dash, and that A dash is going to repeat the B, C, S dash A, B, C, S dash A dash, or epsilon. This will be in the final answer. Okay, this is second. So combine 1 and 2, you will get the final grammar which is free from left recursion. That's all. You know how to eliminate for two non-terminals, then you can apply the same approach for any number of non-terminals. Okay. Now we have very simple example. Identify the equivalent grammar after elimination of left recursion. This is a kind of example you may predict in the exam. So now you see you have two non-terminals, right? Now you can observe which one is going to be the best option. Now you have two left recursions. This is capital A, right? S derives capital A. This is a like non-left recursive term. So in the step 1 you have S derives A, S dash. As these are only non-left recursive terms, what is S dash does? It will repeat A and B using right recursion, and S is done. S is done. But when you are doing capital A, you need to substitute. Do you have any S here? No. Substitution is not required. Substitution is not required. So directly eliminate left recursion. Job is over. So in the step 2, you are not needed to substitute anything because there is no capital S. There is no capital S in A productions. Fine, directly eliminate it. What happens? A derives B A dash. And what is A dash? That is small a dash or epsilon. Now look at which one is matching and see that S, in place of S dash they can take any new non-terminal. No need to take S dash. They may take X if they want it because they have taken X here. So AX. Here AX, there are, this one is XA, so we don't choose it because not S dash A, it is AS dash. So there is a possibility of one of this. Let's see. Next, S dash. Assume X is what? Here X is assumed as S dash. Okay, just I am assuming now. S dash to AS dash, BS dash, epsilon. That's fine. Now here A dash is assumed as Y. So here A to BA dash and A dash to AA dash epsilon is exactly matching with the first line. And what about this line? What is the mistake? They are having left recursion here. We want to eliminate left recursion, right? So C is wrong and A is wrong, B is wrong. A is only the correct option. Okay, you can just match by keeping X and Y respectively S with S dash and A dash. Fine. what is left factoring? You know, when you have the left recursion, we eliminate it, but when you don't have the left factoring, we do it. That means the grammar is not left factored, we will convert into left factored. But whereas the left recursion, when the grammar has left recursion, we eliminate the left recursion. So these 2 points you should remember, what we are doing in left recursion, what we are doing for left factoring. So why we do the left factoring? Again, the top down parsers are following leftmost derivation. So for them, left factoring is very important to avoid the backtracking. So when do we perform left factoring? Suppose the grammar has something like CAB or ACD, right? If the grammar is only has the knowledge of one symbol prediction, this both productions are having A here. If my program or my input is beginning with A, then which production should be taken? I have the knowledge of only one symbol. Then it would be very difficult. The compiler cannot guess which production is your string, which production will derive your string. Then it will, it has to choose randomly. Then that's not the program, right? Program never chooses randomly. You should instruct it. Suppose if it's choosing this and my string is that, then you are wasting the time to substitute. You will substitute this and the string is not matching with your string, then it will go to another production. So backtracking is required. To avoid that, we will do left factoring so that grammar will not have such common prefixes. What is the problem with this kind of grammar? You have some kind of common prefixes of maybe 1 length or maybe 2 length or maybe 3 length. More than one production is having common prefixes. Okay. Now when you have the common prefixes, how do we eliminate such common prefixes? Okay, I'll explain for one symbol prediction, but this could be possible for 2 symbols or 3 symbols, okay, because we are going to learn in the future LL1 grammar, so we can look at only one symbol prefix. What is the algorithm is, if you want to do left factoring on this grammar, left factoring. That left factoring is a concept or algorithm that eliminates common prefixes from the above grammar. Okay, before doing this, ensure that the grammar has no left recursion. Grammar has no left recursion. Then you apply the left factoring. If the grammar has left recursion, first eliminate the left recursion, then do the left factoring. So left factoring is nothing but it's eliminating common prefixes. Now what we get here, S derives, A is there in both the productions, so you keep only once. Now I need to take a new non-terminal that will take care of the remaining portion. Like I'll take, let's say, X. What X does is going to derive these 2 productions, the remaining, the suffix, you can say that, either B or CD. And this grammar, the first production, anyhow you don't have common prefix, now only one production, but here if you have any common production, then again you need to apply the same concept on this. If you have any common prefix in these 2 productions, you need to apply the left factoring on this. But right now B and C are different prefixes for these 2 productions, so this is called as left factored grammar. What is this called as? Left factored grammar. And this grammar is non-left factored. So non-left factored, you are making left factored with the help of the common prefixes elimination. So it's a very simple grammar, but ensure before applying this left factoring, if any left recursion you see, eliminate in the first step left recursion, eliminate left recursion in the first step, then the common prefixes you can eliminate. How do you eliminate the common prefixes? If you see them directly, you take the common one, the remaining you can derive with the help of new non-terminal. Sometimes you may have something like S derives A or B, A derives, let's say this here B capital A. Let me write, sorry, C capital A, B D or E F, something like that. Now you see capital A, anyhow there is no common prefix, so this will be then the final answer. you can't do anything with this. This will be in the final answer. You don't see any common prefix here. It's a B and this is E, so no problem. But here you can't compare. Why? Because here non-terminal is there, here terminal is there. Anyhow, there is no left recursion in this, so you no need to eliminate. But what happens when you see in the first place there is a non-terminal? First you take care of substitution. Here you no need to substitute, but here capital A means what it gives. How can I compare this B with capital A? Directly you can't, but indirectly capital A, when you substitute with this two, you may get the small b there. So what you do is, in that, for this you substitute capital E, but not everywhere, only in the first place. Don't substitute here, don't substitute here, only we substitute here, right, this position. Okay, we are going to do that. So don't substitute here. Substitute A at first position, at leftmost position. What happens then? S derives, you take substitution here, B D, A is already there, or E F A, or then this is a B C A. Now you see there is B here, there is B here, and anyhow other production is not having common prefix with other two. Now these two are having a problem, they are having common prefix. So what you do here, S derives B, let's say X. Anyhow EFA is not having any issue, so keep as it is. Now X has to do DA and CA. So what X does here, DA or C capital A. Now this is going to be a new set of productions, and you have this one and this one. Final answer, what you write? S derives BX or EFA, and X productions are DA or CA, and capital A productions are BD or EF. So this will be the final answer. Okay, so very simple when you know how to substitute and how to eliminate the common prefixes. So 3 points you remember: if you have left recursion, eliminate. Second point, if you see the first position non-terminal, first substitute it, then try to take care of the elimination of that common prefixes. That's all 3 steps you remember. Left factoring is done. The grammar is not left factored, we made it left factored. Okay, this is called as left factored grammar. The next topic is the first and follow computation. If you are going for the top down or bottom up parsers, then these two computations are very important. First computation, the first set computation will talk about who is going to be the first terminal that you can derive, and follow set is going to help us to compute who is going to be the next symbol is the first, next symbol is the in the follow set. Next symbol in the sense who is going to be after me, which terminal that I can derive as a first symbol after me, like who is following me. That's very important to know. Who is possible to derive from me. From me is going to be the first, after me is going to be the follow. But anyhow, from me I want first terminal, after me also I want the first terminal. Anyhow both of them are going to look at who is going to be the first terminal that I can derive. But within me or after me, both are going to be different. In the first set, we will look within that productions, and follow set we will be looking at after that non-terminal. Anyhow, it's very simple, we will look into it. What is the first set and follow set computation? Okay, let me help you with example. Very simple example. Okay, in the beginning we don't look at all definitions, but just one small example. Okay, here we will look at the first concept. Here we look at follow set. suppose I have, let's say X is a non-terminal which has two strings, let's say A, B, C, D, E. That if I am trying to compute the first set from X, what happens is you will get A and D. How did you get that? Because what X can derive only two strings, A, B, C, D, A, D, E. Right. I am writing directly strings, but in general the grammar, in the grammar here you may see a lot of non-terminals, here you may see a lot of non-terminals. Then you need to look at who is going to be the first terminal from this production and from this production, and that is going to be A. Here directly you can see, but not all the time. If you see there is a non-terminal, then you should look further what non-terminal does. From there you need to find out in different further levels, and here D. Okay. It is a very simple. If you want to find first of X, compute all the possible the first terminals from that X. For that you should look at all the productions of X, and if there is any indirect computation you should go further and compute it and bring here what it can derive as the first terminal. What about follow set? In the follow set we do not look at suppose if I ask follow of X, follow of X, I do not look at X productions, I look at a production which has X. It means something like this. Do not look at who is there, somebody is there here, do not worry who is there, but here somehow something like A X B here, and here you do not have any X, let us say here somebody is there, and here you have, I do not have any X here, but I see here C X E here, something like that. Okay, do not worry whole what is there in these dots, somebody is there, but I know their X is not there here this side. Okay, here it could be anything, let us say any non-terminal. Here other than the X you have some sequence, you do not have the X within that sequence. Then how do we compute this follow of X? Here X is there, who is after X? Small b, but do you see always a terminal here? No. Then we will learn how to compute. If you see non-terminal there, you need to have some kind of substitutions to understand. Similarly, who is after this X? That E is the follower. So when I am trying to compute follow of X, you should focus on how to get this B here, how to get this E here. If we do not have this B and E, we have mechanisms to compute. Okay? So this is nothing but follow set. Anyhow, the follow while you are computing, you should look at whole grammar. But when you are computing first set, you purely depend on this X productions, and whether you depend on the whole grammar or not, these two productions will talk about it. So mainly these two productions, if you see any non-terminals here, further you go and compute. If not required, then directly you got the answer. Okay. First set, follow set, both are nothing but set of terminals, but this set of terminals are derived from X, this set of terminals derived after X. Here from X the first terminal, here after X first terminal. Is that clear? From X the first terminal, after X the first terminal. Here you look at only X productions, here you look at all productions in the grammar where you have X within the production. That is also RHS side. Okay. That is a first and follow. A definition: what is the first of X? Is nothing but, or let me write in theoretical line, or I will write mathematical formula, do not worry about it. T means terminal, T is a terminal. I want every T. T is a terminal which is derived from X, derived as first symbol from X, from X. How do you specify that? It simply like X derives T followed by alpha, that is the meaning. Where T is derived as a first symbol, then you take that T and put in the set. Every T we are going to put here. Okay. Simply I am writing another way, T is such that x derives T alpha, that is it. X is a non-terminal, from that you are going to derive T as the first symbol. Alpha is any, alpha is any. So, I have written some kind of formula here. What is a follow of x? I will directly write a formula here. I want a T where I do not care what is y, but you have alpha and you have x, then immediately you will see the T. After that you may have anything, does not matter. So, understand here what I am focusing on. I want this T, but that T is present just after x. Somehow it present, you need to compute with the rules. We are going to look at that examples too. So, I want to compute the x, then after x who is there, you have to look at whole grammar. Does not matter who is left side, only you look at this production where you have x, after x you have a T. So, every production who is having x, you need to compute the T after that x and put the T in the follow of x. Anyhow, I have explained with example, I have given a definition in terms of mathematical set. You can also write in English language what is the first and follow of x. Okay, let us practice some of the questions quickly. First example, S derives epsilon. Then what is the first of x? Sorry, first of S, simply epsilon, because no symbol possible to derive. So, this is a special terminal for us, special string, it is a string, we do not have any terminal to derive, so we keep epsilon. What is the follow of S? S is not there in the RHS side, but S is the start symbol, we keep dollar as the special terminal which follows S always. So, S dollar always there, right. When you have something here, that is S, whatever it derives, at the end of the program we always keep the dollar. So, this is a very important concept where dollar belongs to follow of the start symbol always, remaining may or may not present, but this is always. S might have other terminals, but dollar always there in the follow of start symbol computation. That is the first example, and keep that point. S is the start symbol, then dollar must be inside the follow of S. Second example, second, S derives, let us say ASB or epsilon. Now, how do you compute the first of S? What is the first of S? You have very simple A here and then nothing, epsilon. So, A comma epsilon. First of S, what S can derive? Either A can derive or no one can derive, that is epsilon. What is the follow of S? Without looking at the grammar, you keep the dollar because S is the start symbol of the grammar. So, dollar always present in the follow of S, dollar always present in follow of S. Then in the grammar, do you have S anywhere in the RHS side? Yes. Then who is after S? B. So, we are going to write a B there, that is it. Okay. Let us go to another example to discuss more. Third example, S derives BA or A and A derives ASB or AD or F, something you have. Now, what is the first of S? Then what is the first of A? Once you compute, then you go for follow of S, then you compute follow of A. In the exam they may ask only about one non-terminal, that could be so easy. So, here we have 4 questions. In this, what is the first of S? You got a B and E. So, directly you can put them. When do you have an issue? When you see their non-terminal, then indirectly terminals will come. But here it is so easy to compute. Now, what is the first of A? Here you will have a problem. Small a, small f you can compute easily because you see the terminal there, but here A is there. When there is a non-terminal, it may take time if that capital A has a lot of productions. But here is might be so easy. If you look at a capital A, again you need to substitute this 3 only, yes or no? Again you need to substitute this 3 only at this point. When you put all these 3 here, either you get A or F in the beginning or this AD here. Again same, right? So I can stop here. But sometimes if this capital A is deriving epsilon, then this D might come here. Luckily we don't have epsilon here, that's why you are not going to this D. But this D you may get when this capital A derives epsilon. That's a very important point. But right now I can close with this. I can close, I can say only AF comes whatever you derive with capital A. And now follow of S. Without looking at the grammar, S is the start symbol, so I know I have to put the dollar. Now you need to look at all the productions. Where is that S? Can you tell me? Where is S? You have S here. That's it. So what do you get here? B. So I am writing a B here. First one is so easy. Second one, follow of A. In this, where do you have A? You need to note every point. See, you have A here, you have A here. 2 productions are having capital A. That means you should focus 2 times separately, then only the answer comes out. Remember that? Each production is so important in the computation. Out of this 2, I can see this production is so easy because D is visible, so you get it. But other production, nobody is there after. It means if nobody is there after, it means you should compute who is after S. Why is that? See, yes, you have, let's say, alpha. When you substitute S with BA, you will get the same thing, right? You are asking who is after A, but nobody is there. It means it depends on who was substituted this A. If you want to find out this, just find out who is after S. So very simple. When you have a non-terminal at the last, you want to compute who is after that, just compute who is after LHS. Very simple. So you get here simply D union follow of S. You already know that, right? Follow of S. I am just writing short form FO of S means follow of S. What is the follow of S? Already computed. So that is T dollar comma B when you do the union. Fine. So we have a new concept here. What is that new concept? When you see something like this, X derives, somebody is there, here Y is there. Now you want to compute who is after this. You want to compute here. Then follow of Y, you should say that depends on follow of X. We keep this point in mind. If you are looking to compute the follow of this Y, but nobody is there, so you should compute follow of X. That's it. With this, you are very clear how to compute the first and follow. Now introduce some null productions possibly. Fourth example, S derives SA or SB or epsilon. See, how do you get now first of S? First of S. When you look at that, epsilon is very clear to you because directly it is a production. But in this 2, here S means non-terminal. What is there? You can only put epsilon or other productions. But at any cost, if you put epsilon here, you get A as the first symbol, like SA. Here you put epsilon, epsilon A is nothing but A. A is going to come as the first symbol. Similarly, B is going to come as the first symbol. Here A or B only possible. Okay. Anyhow, there is no other terminal to write. So you can focus on what you can derive there. Now what is the follow of S? Follow of S is having dollar always, due to S is the start symbol of the grammar, and then you look at who is after S. A is there, B is there. So these 2 S you have to focus. A comma B. That's it. There is another way to compute, another concept. When you have epsilons, you should deal carefully to compute the first sets. To compute the first sets, also you should be careful to compute the follow set. Fifth example. Suppose you have S derives A, B, A, B, C, A derives AA or epsilon, B derives BB or epsilon, C derives C, D or epsilon. Okay. So, what you do is, for this fifth question, take it as homework and practice what is first of S. Similarly, what is the first of A, what is the first of B, and what is the first of C. So, compute, similarly you compute follow of S, A, B, C. So, we will get to know a lot of concepts here, remaining previous 4 problems, all the computation that you have done will be useful here. Okay. Similarly, you compute follow of S, the follow of A, follow of B, follow of C. Okay, let us practice the computation of the first sets for this grammar. What is the first set for E, R, T, Y, F? Now, look at this grammar, it should be easy to compute the first of E. See, always you just look at what E can derive, T followed by R. So, first look at a T. Is that T giving epsilon? If not, then T has the answer. So, T is depending on F, because T derives F. Look at that, E depends on T. When I am going for T, it depends on F, and when I go for F, it gives open parenthesis Ri. So, answer you got very clearly open parenthesis I. You should be very careful, in case if you see epsilon anywhere, you should go further to compute the terminals. Okay. Next, first of R, first of R directly plus here ash is there, so easy to compute. Next, first of T, what is the first of T? F. What F can do, just now we have seen, right? That is open parenthesis comma I. And what is the first of Y? Star and ash. What is the first of F? You already seen that, directly you can get open parenthesis and I, open parenthesis and I. That is it. How easy to compute. When you have epsilons, it may take much time, but when you do not have null productions here, it could be easy to compute. It could be easy to compute. I can say simply, first of E nothing but first of T, first of R nothing but plus ash, and first of T nothing but whatever does F, first of F, because I am very clear here there is no null rule. When there is no null rule, directly I can say here first of T nothing but first of F only, and first of Y nothing but star ash, first of F nothing but open parenthesis I. But when you have epsilon, in case this F is deriving epsilon, then answer also depends on Y. If there is epsilon here, answer first of T also depends on Y, because F might be substituted with epsilon. Okay? So, remember this point. Next question is computing follow sets. Okay? Computing follow sets. First computation follow of E. Let us do one by one. When I am computing follow of E, your focus is only on E. Clear? So in this grammar, do you have anywhere E? Yes, you have one place. See, I am looking only right side. I don't look at left side E. Okay. In this whole grammar, only here. Before doing anything, this E is the start symbol. So I keep the dollar. How do I know? Because that is the, these are here not mentioned, but the first production, the set which is defines the start productions. Now after E, who is there? The first terminal, right parenthesis. That's it. Over. In whole grammar, you have only E at one place in the RHS side. So answer is so easy. That's the first. That's the follow of E. Next, follow of, let's say, R. Now onwards, you should look at all the productions. Where is the R here? There is a one place, there is another place, right? One thing is so easy to discuss, that is this R again depends on R. So you can ignore that. You can ignore this because this R we don't compute. But this R, follow of R, we don't have anything, means follow of E. But follow of E already computed. If not, wait for some time. If not computed, wait for some time. So follow of E is nothing but dollar comma right parenthesis. So we got what is the follow of R. The second production is follow of R, nothing but again R. So we don't need to compute. We don't need to compute. So we got the answer for follow of R. Follow of T. What is follow of T? You look at the T's in the right side. This is the first T and this is the second T. That's all we have. And carefully look at here after T R is there, here after T R is there. But don't assume both are same. For this grammar, both are same. Reason is here R is deriving always a terminal. In case R deriving epsilon, that means T after T nobody there. There is follow of T is follow of E. Here follow of T means follow of R. In case R derives epsilon. In this example, R always gives something. That's why follow of T nothing but first of R in both of them. But it is not always. In case first of R is having epsilon, then T also required to compute E. Remember this point. Okay. The follow of T, somebody can conclude first of R only because R is always deriving something. We just did that. That's a plus R hash. In case if you see epsilon here, in place of hash, if you have epsilon, then this R can be substituted with epsilon, then T might depend on E, T might depend on R to compute the follow sets. What about follow of Y? Okay, here follow of Y. See, every time I mark it, I compute. That is the best way to do the follow set computation. Here Y is there, here Y is there. The follow of Y depends on Y, you can ignore it. But this follow of Y depends on follow of T. So I am writing directly follow of T. As I already know what is follow of T, so you can copy paste. If not, wait for that T computation. Follow of T is already computed plus comma dollar. That's about follow of Y. And next follow of F. Follow of F. What is the follow of F? What is the follow of F? You have one F here, that's it. Now here, sorry, second F, any other? Okay, look at it carefully. So this two F. Both the times follow of F means first of Y. So immediately depends on Y. Is that Y always gives something in this grammar? Yes, Y always gives star or hash. That means it's in case if Y deriving epsilon, then this F might depend on follow of T, this follow of F might depend on follow of Y. But right now, both the productions follow of F nothing but first of Y. But first of Y you already computed previously. What was that? First of Y nothing but star comma hash. Done. Okay. So you may try something like in place of hash, take epsilon and do the homework. Right. In place of this two hash, put epsilon here and here. Then look at how the first set and follow set can be computed. Okay. Do that on as homework. and you may discuss in case if you have any doubt in computation of first and follow set. With this, we have learned all the basic concepts required for syntax analysis. Now, in a sense, you are actually starting the parsers now. What is the parsers? What is the parsers? Now, we have many types of parsers. Mainly, we learn top-down parsers and bottom-up parsers. That's it. In the world, you have various other parsers too, but we will learn only these two types of parsers as per the syllabus. In the top-down parsers, we will mainly focus on LL1. You are interested to learn any other parser, you can learn, but for the exam point of view, LL1 is very important. Bottom-up parsers, you have LR parsers, and other one you have operator precedence parsers, OP, operator precedence parsers. I can write OP parser, operator precedence parser. Here LR parsers, again you have many other types. Here you have like LR0 and SLR1, LALR1, another one LR1 are also called as CLR1. The operator precedence parser, we have only one that we will see. Now, these are the important parsers for our topic. First, let me help you. What is this top-down parser? Top-down parser, it actually follows leftmost derivation. It uses leftmost derivation to derive a string. It uses leftmost derivation to derive the string. And this top-down parser, especially we have many types. Among them, you may use recursive descent or non-recursive descent. Two types we have, recursive descent a parser or non-recursive descent. There are two types. Recursive descent and non-recursive descent. If it is recursive descent, we use some kind of procedures to understand how each production can be used. If you are following non-recursive descent, you build a table, LL1 table or predictive parsing table for this. This is basically table approach. You need to design a table to understand. Here is a procedure oriented procedures we write, functions, procedures we write for each production. You write a procedure for each production, you build a table for whole grammar. So, this is how you build, you use recursive and non-recursive descent. Especially we use, by default we use LL1 to understand. By default LL1 parser we use as a top down. This LL1 parser can be implemented as recursive descent or can be implemented as non-recursive descent. So, this is the practical approach and this will be the theoretical approach. This LL1 parser is called as many names, like it is top down parser. You can say that by default top down parser is LL1 parser. It is a predictive parser. It is going to predict the one symbol ahead. This is a prediction. Predictive parser, and it is, you can implement either recursive, non-recursive descent. If you are using the table, that is a non-recursive. If you are using the procedure, that is recursive descent. Okay. These are the definitions of top down parser. And here, what is this LL1 parser? That we are going to look at in detail soon, but before that we will look at what is this bottom up parser. What is the bottom up parser? Top down parser you understood, right? It follows leftmost derivation. Then what is bottom up parser? What is bottom up parser? It follows RMD, rightmost derivation, in reverse order. Then we should know what is the rightmost derivation in reverse. That's called as the bottom up parsing order. The bottom up parser also called as shift reduce parser. Why? Because the shift reduced or reduce, fine. SR parser, basically we are having two actions, shift and reduced actions. We have only two actions, shift and reduced actions. When you look at this bottom up parsers, by default CLR1 parser, but you know bottom up parser has many variations. We have LR0, we have SLR1, we have LALR1, and we have CLR1, also called as LR1, and we also have operator precedence parser. That's fine. Why always LR is there here? Because you see there is LL1, now here you have LR followed by 0 or 1 something, right, 0 or 1. This L, there are both of them, there is L, right. So this means left to right scanning in both of them, left to right scanning. You have only same left to right scanning, but here this L means leftmost derivation it is going to follow. This R means not rightmost derivation, it is reverse of RMD. RMD in reverse. Don't say RMD, say RMD in reverse or reverse of RMD. The 1 is the prediction, 0 means no prediction. Now we have like SLR 1, 1 means we have one look ahead, S means here simple. And you have LALR1, here this LA means look ahead. Another one CLR1, C means canonical, C means canonical. So that is how you name them or you speak them. What is LR, what is SLR, what is LALR, what is CLR. CLR also called as LR1 here. Fine, you know simply instead of writing SLR1 you can also call SLR parser. Instead of calling LALR1 you can call simply LALR. Instead of calling these things just call LR, that's fine, or call CLR, that would be fine, LR or CLR, because they are standard names for them. In the exam they may have simply SLR, so you know that it is SLR1, but this one you just don't say LR. LR0 is a theoretical concept which will help us to understand other three. In the bottom up parser we also have operator precedence parser, but this CLR1 is the default parser and it is a more powerful parser compared to other three parsers here. Okay. Now this is about the bottom up and top down parsers differences. In the top down we use LMD, bottom up we use RMD in reverse. Okay. It was one of the gate question also, bottom up parser. Instead of bottom up parser they asked LR parser follows dash, then you should answer it RMD in reverse. In LL1 parser we will be having the LL1 grammars. So if you want to construct LL1 parser you require LL1 grammar. So with the help of LL1 grammar we construct LL1 table. Once we have LL1 table you can use the table to understand the given string whether it is syntactically correct or not. So this is idea how you do it. We may have your program that you may call it as input or something like that. So this is LL1 algorithm, let us say, and it uses basically a stack to understand. You require stack, and what you need here, the table. You may call it as LL1 parsing table. This is overall LL1 configuration, the parser configuration. You build a table, and use the algorithm to understand whether the given input is syntactically correct or not. So, this table stores the whole grammar. That means LL1 grammar is stored in this table. If you want to verify this input is syntactically correct or wrong, then this table will help you. So, to build this table you require first and follow set computation, then you can fill the table with the productions. So, first we will understand how to construct the LL1 table. Later on you may focus on how to parse it, but for the exam point of view LL1 grammar and LL1 table both are important. Now, how to identify LL1 grammar? You require LL1 grammar, right? But how do you identify the LL1 grammar? You have some shortcuts, but I will just write theoretically how you write LL1 grammar. First you take unambiguous grammar. If you do not have unambiguous grammar, you cannot write LL1 grammar. If in case if you have ambiguous CFG, you should know how to eliminate the ambiguity, but there is no algorithm directly elimination of ambiguity. So, you should know how to write unambiguous CFG. Once you write it, then somehow you eliminate left recursion, make a non-left recursive grammar, because left recursive grammar is not allowed to implement this LL1 parser. Make somehow non-left recursive CFG with the elimination of left recursion. Once you have this, you know you should eliminate common prefixes to make left factored. So, make the grammar is left factored. This left factored grammar is basically called as LL1. So, this grammar finally you see it is LL1 grammar, but this LL1 grammar you can understand with the help of the table. If you build the table, you will get to know the given grammar is LL1 or not. So, after doing all this, then at this point of time, once you have the left factored grammar, then you build a table, there you can understand grammar is LL1 or not. In case if you do not have null productions at this point of time, directly this grammar you can say LL1, but in case if you have null productions here, then after building the table you will understand, oh, this grammar is LL1 or not. So, these steps are very important. Take an ambiguous grammar and eliminate left recursion to get non-left recursive CFG, eliminate common prefixes to get left factored CFG, and construct the table to understand the given grammar is LL1 or not. So, these are the steps to understand or how to identify or how to write LL1 grammar. How to write or how to identify LL1 grammar. So, you should not have ambiguity, you should not have left recursion, you should not have common prefixes, and when you build a table you should not observe certain properties like a single entry should not have more than one production. So, that is what you have to identify the given grammar is LL1 or not. Fine. You have a shortcut to do that. You no need to look at ambiguity, left recursion and common prefixes, because you also have a shortcut to identify the grammar. Now, how do you construct the table? Let me take a simple example. I am just taking A as B or C as let us say D or epsilon, only one non-terminal. How the table is constructed? The table is something like you have S is a row, only one non-terminal, but how many terminals? 1, 2, 3, 4. So, A column, B column, C column, D column, and special column is for the dollar. This is a table. How do you construct this LL1 table? If there are 2 non-terminals in the grammar, there will be 2 rows. If there are 100 terminals, then 100 terminals should be there. Epsilon we do not keep as a column, okay, and dollar must be there assumed as end of the input or end terminal, special end terminal. Now, first compute the sets, first set as well as follow set. You do not compute the follow set if you do not see the epsilon in the first set. Suppose first of S do not contain epsilon, then you do not need follow set. Follow set is required only when its first set has epsilon. So, if you have 3 non-terminals in the grammar, you no need to compute the follow set for every non-terminal if its first set is not having epsilon. In case the first of S has epsilon, you should compute follow set of S. If the first of capital A is not having epsilon, then don't compute follow of A. So, you compute follow set only when its first set has epsilon. So, that is a very important point. First of S is having here A, C, you have epsilon, that is the reason you require to compute follow set, otherwise we do not need follow set for S. Here follow set of S, by default dollar, and here S after S B is there, here after S D is there. Now, why did you compute? Because of only this epsilon we are computing the follow of S, otherwise we do not compute. The reason is, if the first of somebody you are looking but you do not have anything, then immediately we will go after that non-terminal. That is the reason, when the first giving if the first is giving nothing, then you need the follow. If the first is always giving something, you do not need follow. Okay. This funda is very important. Now, let us come to the first of S. First of S, you just look at S comma A and S comma C, two combinations, S A. In this S A, look at S productions only. In this S row, you will be having S productions, that is all. If there are many non-terminals, you should know that in this row you will be filling with only S productions. Okay. S, how many you have? 3. Among these 3, how many productions are giving this A as the first terminal? That is it, because you are looking for SA. This one is giving A as the first, this one is not giving A as the first, this is a null production. So, you are going to write this production, either you can write only RHS or you can write whole production. I am only writing like ASB. RHS is sufficient because it is S row, I know S derives ASB. So, S derives ASB. So, I don't need to write LHS, because LHS is already name of the row. Fine. Next, S comma C, that S row and C column. Out of these 3 productions, which production gives C as the first symbol? This production. So, we write here CSD. Very clear. Now, this is over. Because of this epsilon, we are having these 3 terminals which are coming after S. That means, now you have to look at S comma dollar, S comma B, S comma D. These are especially for null rules. But null rule, here you can see directly, that is why you can write epsilon in these 3 columns, dollar $B D, dollar epsilon or S arrow epsilon, both are same, epsilon and B epsilon, D epsilon. When I look at this, I do not have any entry with more than 1 production. Some of the entries you may have 0 production, that is fine. But if you see any entry more than 1 production, then the grammar is not LL1. But here every cell you have either 0 or 1 production. Anyhow, you have 1, but actual definition is every entry. If you see at most 1 production, then this grammar is LL1. Okay. This is one way to identify. Now, I can conclude that I am able to build LL1 table successfully without having any conflicts in the table. So, this grammar is LL1. Okay. This grammar is LL1. Let us take second example, look into it. S derives A, S, A or epsilon. In case if you try to observe the left recursion, no left recursion. If you try to observe any ambiguity, there is no ambiguity here. So, it is unambiguous grammar. If you try to observe common prefixes, this is epsilon, this is A, no issue with the common prefix. Now, still it is not LL1, Remember, if you are thinking about only ambiguous and left recursion and left factoring concepts, not enough. Sometimes because of this null production, it could be possible not LL1, right. If it is not having null rule here, definitely LL1. Because of this epsilon, there are 3 concepts: unambiguous, non-left recursive grammar, left factored grammar. Those 3 words are not sufficient now. Okay. So, any grammar which is unambiguous, non-left recursive, left factored, you cannot guarantee it is LL1. Okay. But if it is LL1, it must be unambiguous, it must be non-left recursive, it must be left factored. Okay. Now, why this is not LL1? Try to understand the first and follow set quickly. What is the first of S? What is the first of S? Which is A comma epsilon. What is the follow of S? Why do you want to compute? Because epsilon you have. So, what is the follow of S? Dollar, and after S A is there. Now, try to build the table for this. You have only S row and only one terminal dollar. Now, look at first combination, very important, SA. What is that SA production? Out of this two, which production will give A as the first symbol? This one. So, you write here ASA, one production you have written, and because of this epsilon you need to look at S comma dollar, S comma A. S comma dollar you write epsilon, and S comma A you write epsilon, null rule. See, in this entry you have two productions, S derives ASA, S derives epsilon. That means the given grammar, this one is not LL1, this is not LL1. Now, this is the best example for you. Anybody was assuming that the 3 points, unambiguous, non-left recursion and left factored, these 3 words are not sufficient to say it is LL1, to say it, because even though it is unambiguous, no left recursion, no, it is left factored, still you are not able to say LL1. Okay? So, this is the best example I can say, but whenever the grammar is LL1, those 3 points always holds. Fine. So, you have multiple productions in the same entry. That is why this table is not allowed LL1, but you tried to construct the LL1 table, but you can't say now this is LL1 table to proceed further because of some ambiguity. So, you got to understand, right, how to construct the LL1 table. How to construct LL1 table? What is the approach? First you compute all first sets, then compute if required follow sets, then look for fill the table. You make some table and the table entries, you fill the table entries. How do you fill that? With the help of first set and follow set. So, this all the 3 you are going to do, and this is optional, not compulsory. Follow set is computed only when the first set has epsilon, otherwise not required. Okay. Now, you can see this table. Very simple question I have here for you. I have given you LL1 table. This table has already stored the grammar, right, using the first and follow set computation. Now, by looking at this table, can you write the grammar back? Yes, possible. When you look at this table, you only store the productions, right? When you look at this table, 1, 2, 3, 4, some productions might be repeated, it is fine. But when you look at the S row, S arrow, A or BB, if anything is repeated, do not write twice, just one time is sufficient. When you look at A row, A arrow B, that is it. When you look at B row, B arrow C. That is all. This is your grammar. For this grammar, you might be created this table, and this table is used for parsing with the help of LL1. Now, look at which one is S has 2 productions. S has 2 productions. Oh, here A, here BB, here BB A. That is fine. BB A. Any order you can write. A has only one production, and B to C has only one production. So, C is the right answer. Very easy, right? This kind of questions can be easily identified. Another kind of question is, sometimes grammar will be given and this table will be given. They might ask what is here, right? In place of this one, they may not give you what is it. Then you should know how to find that. How do you find? Just compute first of S, if required follow of S, but do not compute first of A, first of B, because when the S entry they have asked, S row they have asked, then focus on only S. No need to focus on A and B, because A and B are not there in the options to right to fill. So this is very important. Compute first of S, required follow of S. Then look at the combinations to find which production should be there. Okay, that's one good question for the exam point of view. With this, we have completed LL1, and very few questions we have in from the LL1, but it's a very important the tables and how to identify LL1. I have explained LL1 theoretical concepts. You also have a shortcut to learn, and then we'll go for bottom up. If you look at it in the exam, LL1 you see computation of first sets, computation of follow sets, and table filling. If you miss any entry in the table, then find out what is the entry correspond to the table corresponding combination in the table, and then they may ask you to identify LL1 or not. And what else they may ask here in the LL1 about left recursion or about left factoring concept or about ambiguity. Then when you go for bottom up parser, mostly theoretical questions like identify is this LR grammar or not, or compute the closure or go to. Very simple questions we will be having, or find relation between different LR grammars. Fine. Now bottom up parsing. What is this bottom up parsing? Bottom up parsing, I told you have two types of mainly LR parsers and operator precedence parsers. We will be focusing on first LR0 parsers. But how do we learn this bottom up parsing? We'll first try to understand the LR0 items, so that you will get to know what is this item, how the production is converted into item. Once you know what are these items, we'll go for computation of the closure and go to functions. These two will help you to construct the diagram. Before constructing the table here, we need a diagram. So here we'll try to construct the LR0 DFA. We call that DFA diagram, and then we'll try to understand the LR0 conflicts like SR and RR. We have two types of conflicts, SR and RR conflicts. The same thing we will go for now. After this, we will get to know the given grammar is LR0 CFG or not. You can identify the grammar is LR0 or not. Then after that, one after other, how to identify SLR1 grammar with the help of construction of the DFA, and similarly LALR1, CLR1. We will go first LR1, then we will go for LALR1, and what is the relation between all of them. And ninth topic after this, you will go for operator precedence. How do you compute the precedence of the operators with the help of operator grammar? Okay, these are the main topics that you will see in the bottom up parsing. Okay, first we should know what is this LR0 items. Okay, LR0 items. But anyhow, you are aware of this LL parser configuration. Same way, you have a stack that you have seen in LL1, and you also have here some input that you write. It's a sequence of tokens basically. Okay, sequence of tokens here. Here LR algorithm. This algorithm is same for all. You may say bottom up parsing algorithm or LR algorithm, as you are talking about LR parser. Simply you say reverse of RMD. What is this LR algorithm? Reverse of RMD. And here the table will change from parser to parser. Here table, LR table. This table could be LR0 table or SLR1 table or LALR1 table or LR1, CLR1 table. This table keep on changing for the one to other grammars, but this algorithm same for all. There is no change here. The input you give, and with the help of this table, it's going to parse. It's going to verify the syntax of this input. Now the challenging is how do you build the table. So whenever you are able to draw the DFA, which is equivalently you will be having a table for it. So we are going to learn the DFA for all these four, and we relate all of them. In case if you want to learn how to construct the table, how to parse with the help of algorithm, that takes a little bit time and not much important for the exam. That's why in this series I will not be covering the 2 points, that is how to construct the table. Theoretical points are very important anyhow, and what is an algorithm. This little bit extra time needed for you. Fine. As I told, I will be helping you first with LR0 items. LR0 items. What is LR0 item? Basically, LR0 item means you will be having dot in the RHS side. So here this dot will help you to track, to check the status of this production, how much is passed so far with the help of reverse of RMD. So during the parsing only you will understand what is the use of this dot. Suppose you have very big production, something like A, B, C, something like that. What happens is it starts dot here, after some time it moves here, and after some time it moves here, after some time it moves here, after some time it moves here. When it goes when it goes at the end, when it is going to appear at the end, that means this production can be reduced further. Reduced means, oh, this RHS can be replaced with LHS. So that's why it's able to understand the reverse of RMD concept. What is reverse of RMD? Basically, top down parser, what it does is, if you give S, let's say ABC is my string or my program, it is trying to derive. But in bottom up parser, if ABC is your program or input, it will take the program, it will try to convert into S. But how this bottom up parsing works? Top down parsing, anyhow you substitute and you get ABC at the end using LMD concept. But this ABC, how you convert into S? For that, we keep track of this something. We keep the dot here. After some time, you might have A dot BC, you don't know that. Somehow this A is converted. After some time, you may have, let's say, AB dot C, and after that, this might further, let's say, X dot C, and after that, maybe XC dot, and then after that, it might be S. You do not know how the grammar is there, right? The grammar is going to decide how this dot moves further and when to reduce to somebody else. If this is, let's say, A, and this A, when dot moves from here to here, then small a is replaced with capital A. If there is a production, A derives A, and you found that this dot is at the end, that is reduction will happen. So it's a very big process. At this stage, I don't want you to think about all these things, just focus on this production. What is this item called as? LR0 item. Why? Because dot is there in the production, in the RHS of the production, that's called as item. LR0 item, because I don't maintain any followers here. This is called as LR0 item. In future, you will do something like dot is there, and also comma, you will maintain some lookheads like L1, L2, something like that. Then this is called as LR1 item, that the one prediction after this production, if any terminal following, then we are going to track them. We don't compute who is a follower of X. Directly we will keep who is the follower of X with the help of the productions that you track. So this is basically LR1 item. This is called as LR0 item. LR0 items we use in both, with this kind of grammars we use in LR0 construction and also SLR1 construction. But this LR1 items we use in LALR1 as well as in CLR1. You can just remember now, the LR1 items will help us to understand or to construct the diagrams for CLR1 and LALR1, and LR0 items will help us to construct LR0 and SLR1 parsers or diagrams. Fine. This is about LR0 items. But now let us talk about more LR0 item. Okay, let me take some example. Suppose I have X derives A, B, B. Okay, very big production, that's fine. This is production. Now, if I want to write as an item, how many ways I can do that? At some point of time, I may have A, B, B. After some point of time, I may have A dot A, B, B. After some point of time, I may have AA dot BB. After some point of time, I may have AAB dot B. After some point of time, I may have AABB dot. See, all are called as LR0 items, but they are in different instances while deriving the string using reverse of RMD, and you are tracking basically here. Now, what is that each item called as? Anyhow, it is LR0 item, but this based on the status, you can keep the name. See, after dot, who is there? A. After dot only, we never look at before dot. After dot, who is there? A. After dot, capital B. After dot, small b. After dot, no one. Speak again. After dot, who is there? Terminal. After dot, non-terminal. After dot, non-terminal. After dot, terminal. After dot, no one. After dot terminal is there, that production or that item is called as shift item. So, this item is called as shift and this item is called as shift. So, this one as well as this one is called as shift items. Why they are shift items? Because terminal present after the dot. Just after the dot, immediate symbol is the terminal. And in case if you see non-terminal after the dot, this one and this one. This one as well as this one. Both you see that after dot there is a non-terminal. So, we call it is state item. That basically helps us to make the go to entries. So, you may say go to item or state item, it is very interesting name. It helps us to make go to entries. Shift item will help us to perform shift actions by giving shift entries into the table, and especially this one after dot no one. So, you can say this one is called as a reduced item, also called as completed. Whereas, other two items are incomplete, the dot is not at the end, somewhere, right, other than at the end. These four items are called as incompleted, either shift or state, depends on which symbol is there immediately after the dot. Immediately after the dot is terminal, then that is the shift. Immediately after the dot is the non-terminal, then that is called as state item, or you may say that helps us to make the go to entries. Now, we understood what is LR0 item. LR0 items are three types: state, shift and reduced items. This reduced item will help us to perform reduced action. Shift item will help us to perform the shift action. That is why the bottom of parser is called as shift reduced parser. You may ask, sir, what is the state item? That is used internally. Okay, while performing the reduction, these items are going to help us to do something internally. Okay. In case if you learn the reverse of RMD algorithm, we will get to know how the state items or go to entries will help us. There is special grammar now. We have a grammar, first we convert into augmented grammar. You may ask, sir, you did not do that in top down parser, now why are you doing? The reason is very simple. In top down parser you are going from S to let us say AB, but in bottom up parser you are going from AB to S. So, you need somebody to inform that there should be a special symbol to inform that the dot goes when it end, this production will help us that S dash derives S dot, that production will help us, okay, your derivation is over, you have done your job from bottom to up. But here you are starting from S, so you do not need S dash. You are going from bottom, you take your, we take the program, we will try to convert into S. So, this production especially S dash derives S is a special production which helps us, to accept the given input, whether the given input is syntactically correct or not, to understand that this production is needed. Anyhow, this production specially used for acceptance. and this is appended to the given context free grammar, then we call that grammar is augmented grammar. Suppose your grammar is something like S derives AB and A derives, let us say, A. If this is your grammar and append this production to this grammar, then we call whole this grammar is augmented. This is given CFG and we add this old grammar now. S dash derives the start symbol of this grammar, that is S. So now for this, S dash is the start. Who is the start? S dash is the start and this grammar is called as augmented grammar. For this, S dash is the start now onwards. Okay. But what is actually given grammar? That is having S is the start. So for the given grammar, we append a special production. This is S dash derives S, that's it. And then this old grammar is called as augmented grammar. Okay. We always use augmented grammar to construct the tables, LR tables. Now, how to find the closure and go to? Very simple, just follow what I say. Let me take first a grammar which is augmented. Okay, I will just take augmented grammar, which is very simple grammar. Let me take S derives S A or B. So, very simple grammar. Now, that is augmented grammar. We are going to find the closure first. We are going to find the closure. Closure is going to start with S dash derives dot S. So, we are going to find the closure of this one. So, I can say what is the closure of S dash derives dot S. What is it? Then I am starting computation. It is going to give you set of items only. First item is itself. First item is what? Itself. That is S dash derives dot S. But it is going to apply the closure recursively. Here after dot any non-terminal is there. After dot any non-terminal is there. It is going to apply the closure. But how it applies? It is going to include all the S productions here because of this S. If you have a capital A here, of course not there. If you have it, we do not include capital A. We only include S productions. So, remember, because of this S, I am going to add S productions. How many are there? 2. So, I am writing here dot SA, another production is dot B. Now, remember, after dot, who is there? S. Anyhow, S is already added. So, I do not add again. But if you see here capital A, then capital A should be added. If you see capital B here, then capital B should be added. All the productions by placing the dot at the beginning. So, this is a state also called as, it is a state. Maybe you can say I naught because it is the initial state. Its state is nothing but, this state is nothing but I naught, another is nothing but set of LR0 items. What is it? Set of LR0 items. You are going to compute set of LR0 items many times to get whole DFA. And here what do you get? It is just a set. That means state nothing but a set only. But this set is having 3 items. One is S dash derives dot S, S derives dot SA and S derives dot B. That is it. So, either you can say set of items or you can say state or give a label like I naught. So, all are same. So, now onwards I do not write every time set, would be no lengthy, right. So, I will draw the state so that you can easily understand I am just computing closure and go to things. This is a closure, but go to is something from this state. If I do something else, I will get the go to. So, from I naught, it is just like go to I naught by reading something like after dot who is there? S. So, you get something and go to I naught comma I will read S. S already done, both are S only, right, do not do again because it is a DFA deterministic motion. After dot B is there. So, I may compute go to I naught comma B, you will get something. And this already named as I naught, whatever you get here that you can name as I1, whatever you get here if it is distinct you can name as I2. So, this is how we keep on doing it. So, what I do next is only go to. The first time it is closure, the go to computation again depends on closure, but it is called as go to as you are moving from one state to other state. Okay. So let me take this example, I'll do the whole diagram, then you can understand what I am doing here. Okay. So let me take the same example, that is S dash derives S and S derives S A or B. That's it, right? Now it's already augmented, so I'll start here. That's initial state, S dash derives dot S, and always I am pointing here why I am going for the next production, because of this S only I am writing S items here, dot SA and dot B. If you are not interested to write two lines, you can also write like slash dot B. That's also fine if you don't want to do this here. Okay. And here you have S, but this S is already covered here, that's why I am not doing. But when you go to LR1 items, this S both are different. Why? After S dollar might be there, here after S A is there, so you will get different things, and these two S don't consider same in LR1, but in LR0, 0 means I don't have the knowledge, I don't look at who is after, that's why these two will give the same meaning in LR0. And here terminal is there, so you can't expand, so this is initial state, you may name it as I0. Now from this I0 we will expand, go to functions. From here by reading S, what happens, because both are having S, and from here by reading B, what happens. So I0 S you will get I1, I0 B you will get I2. So you can name that later on. I0 S, so these two items will move here because both are having S immediately after the dot. Remember, immediately. Suppose you have ASB, and don't assume this is on S, this should be on A, right? After dot A is there, that on A only they move it. Okay, but for this two immediately S is there, so we will carry. Now here S dash derives S dot, because we are reading S means dot will move to the next. Here S derives S dot A. Okay, this two, and apply the closure on this. After dot no one, so closure will end. After dot small a, so terminal also we don't do anything. We will do only when after dot if there is a non-terminal, then only we will, if this is X, then we will write X arrow, otherwise we never do. If this has to be non-terminal. Okay, so focus on the point I am discussing now. So terminal is there, so no expansion, so close this state and name it as, let's say, I1. And here when I read a B, it moves to the end. When it moves to the end, you can't expand it, so close it. This is called as I2. It's not yet over, because here still A is there. So from I1, the state I1, by reading A, the dot will move to the end. S derives S A dot. Apply the closure on this, there is no expansion, so we will close it. So don't close immediately. You should look at, is there any non-terminal after the dot? So you need to apply the closures again and again. Fine. This is the old LR0 parsing DFA. This is called as finding the closures and go to. Okay. The first we are finding the closure, and then 1, 2, 3. 3 times we computed the go to. So here I can say in one line simply, I'll just write all of them what I did. So I0 here. Okay. Keep here I0 here. What is I0? Closure of S dash derives dot S always. And what is I1 here? Go to of the whole I1. 2 items are there. Go to of I0 from I0 by reading S. What is I2 here? Go to function from I0 by reading small b. What is okay, I'll name it this I3, let's say. What is I3 here? Go to from which state it is? From I1 state by reading which symbol? A. Each one is a set of items only, set of LR0 items. So canon is, you are going to collect all LR0 items. That's why this DFA is very important to construct the table, and is equivalently you have a meaning here, that's LR0 table. What happens when you construct LR0 table? Very simple. If you have the non-terminal, then this is going to help us to make the go to entries. That's why this is called as state representation. And BA, they are terminals, so will help us to do shift entries. If you see anywhere the reduced item within the state, that will help us to make a reduced entries. This is a special item which is used for acceptance. Except this, if you see any production dot is at the end, then that is called as a reduced item. So it will give you reduced entries. But this is a special reduced item, so we get acceptance entry in the table. Okay, in case if you want to know what is LR1, LR0 table, the table will have few kinds of entries like shift entries, go to entries, and then reduced entries, and then acceptance, remaining all blank, you may say that. So few types of entries are there in the LR table. But with this, you understood how to construct LR0 diagram only. And now you should know conflicts, because you constructed the table, diagram. If you don't know how to check the conflicts, you will not know whether this grammar is LR0 or not. If you want to know given grammar is LR0 or not, you should know this diagram whether you have conflicts or not. If you don't have conflicts here, grammar is LR0. In case if you see one conflict any of the states, then it is not LR0. What do you mean by conflict? Conflicts are two types. I'll come back here. Okay, we have constructed, you can take it as homework for practicing, but I'll come to this practice later. Let me explain first conflicts. We have two types of conflicts in LR0. One is SR conflicts. How do you understand SR conflict and how do you understand RR conflict? The name itself is very clear. SR, if a state has shift item and reduced item, then of course remaining we don't care, remaining may present other shift items or reduced items, fine. But if you see at least one shift, one reduced, this together will produce SR conflict. A state should not contain these two items in the same state. In the same state you should never see shift and reduced item. Then if you see, it is a conflict because it has no knowledge after dot what is present, so it will not look at, it will simply say SR conflict in which one? LR0. But SLR1, LLR1, CLR1, they don't say simply conflict, they look for followers, they look for lookheads. Fine. RR conflict means in the same state you see one reduced item, let us say this is a 1, another reduced item, let us say it is a 2, other items may present or not, does not matter, you may have other few reduced items, few shift items, it is fine, but this together will produce RR conflict. RR conflict. In case in your diagram or DFA, at least one conflict is there, RR or SR does not matter, at least one conflict is there, that given grammar is not LR0. So go back and look for the conflicts if you want it. Here, do you have any conflict? If you want to get a conflict, see the names SR and RR, R must be there in both of them. So without reduced item, you don't get a conflict. Suppose you have two shift items, no conflict. Shift state items, no conflict. Shift reduced, yes, SR conflict. Reduced, RR conflict. That means reduced item should be there, other one may be shift or reduced. This is how you should look at. Don't look for the state. Ignore the states, don't worry about it. Look for, do you have any reduced? No. Do you have any reduced? Very important. Say no, because this is called as acceptance. Very, very special. Reduced, but we call it as acceptance. Acceptance item will not produce a conflict because that's taken by us basically. Do you have a reduced? Yes. But do you have any other reduced? No. Do you have any shift? No. That is why no conflict here. Here you have a reduced, but do you have any other reduced here? No. Do you have any other item which is shift? No. So, I can't produce SR or R conflict here. Fine. That is why this grammar is LR0. Why? Because it has no conflicts in LR0. This is how we check the grammar is LR0 or not. It will take time, but sometimes it is very easy to answer grammar is LR not LR0. If the grammar is not LR0, sometimes you can easily identify. How? In case you see ambiguity, that means grammar is ambiguous, definitely it cannot be LL1, it cannot be LR0, it cannot be SLR1, it cannot be LALR1, it cannot be CLR1. Very, very important point. In case grammar is ambiguous, in the exam you can answer in few seconds, it is not any of this grammars I am discussing. Okay. And now let us practice quickly. I have given you grammar, how quickly you can build a diagram. Let us try. First you should start with S dash derives dot S, and S has how many productions? Only one. So, you write here, follow me, dot after dot A is there. So, only A will be included, not a B. So, A. Why A? Because after dot A is there. How many are there? Only one. So, that is dot A. That is all. Do not include this B productions in the initial state. Why? Because after dot capital B is not coming anywhere. So, capital B productions not required. Which productions required? If you see S, you will include S productions. If you see A immediately after the dot, you need A productions. This is the small a. So, you do not need productions for small a because that is the terminal. Fine. This is initial state. Again I am repeating, after dot whatever the non-terminal present, only those productions we include, otherwise no. Okay. Now, from here we will proceed very quickly. S, from here capital A, from here small a. Why only these symbols? Why not capital B here while go to or while taking the transitions? Because we only look at the symbol which is there immediately after the dot. Fine. Can you read the S? You will get S dash derives S dot. You may ask, so previously you got two items here, now only one item, but that depends on what productions are taken, right? Here only S is there, only one production is there with S after the dot. That is why we got only one. After dot no one, so we will close. In case if you see anything after dot, understand should I apply the closure or not. Here S derives, read the A, so dot will move to the next to the A. That is it. We move it and then apply the closure. What happens? Oh, capital B, non-terminal. So, you need to write all the B productions. Why? Because the next symbol is non-terminal. I need them to understand. So, B productions, how many are there? 2. So, oh, it is going bigger. B derives dot AB, B derives dot D. Because 2 productions are there, we keep dot in the beginning. It is not over yet. Why? Because of this B, you added 2 productions, and in these 2 productions also you need to apply the closure again. Here A is there, so A productions should be there. Okay. So, I am just writing here A productions. Okay. This one I will just take later down. A productions because of this A. How many are there? Only 1. And anyhow this is a terminal, this is a terminal, so no need to expand further. So, this is going to be the next state. That means every time you write an item, you should always look at who is after the dot. If you miss, you may miss the productions that need to be added. Okay. Because of this A, you get A derives A dot. Dot is at the end, so no more. Only one production comes here because only A is there after the dot. Only this production has A after the dot. Now, here you can't expand further. Here B, here A, here D, here A. When I read A, exactly you will get the same, you can go there, not a problem. If you are getting same item here, then no need to duplicate, it is a deterministic, you can come here directly. you can always design the better machine or diagram. B, you get S derives AB dot, only one item, that is it. Here when you read A, what happens? B derives A dot B, that is it. After a terminal is there, so you do not go further. And D is only the one, right? Simply you move the dot. And here when you read a B, it goes to end, dot goes to end, over. This is LR0 diagram. How many states are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 states. So when you construct the table, you will be having 8 rows. Here in this diagram, what is the important point is, if I have 8 states, means I get 8 rows in the table. Very important. If I get the 10 states, I will have the 10 rows in the table. Okay. Now, any conflict, any SR or RR conflict, we will look at. Any reduced item, always focus on reduced, because without reduced item, you will never get a conflict. Remember that point. Without reduced item, you will never get a conflict. Any reduced? No. Reduced alone is there, so no problem, because other items should be there to get a conflict. So remember this point. A state, if the state has only one item, doesn't matter which item. If the state has only one item, then there will be no conflict. To get a conflict, 2 items should be there. That 2 items also either RR or SR should be there definitely. Now here no reduced, only one, only one, only one, only one, no worries. Only one, no worries. So focus only on this 2, but no reduced, there is no conflict at all. So I can say this grammar is LR0 grammar, LR0 context free grammar. This is how you answer whether the given grammar is LR0 or not. Construct the table, construct the diagram, look for the conflicts. Look for the conflicts. If you find any conflict, then we say it is not LR0. Next topic is SR and RR conflicts. These conflicts in SLR1 we are going to look at. Already we have seen in LR0, and now we are going to see in SLR1. But here you may ask, sir, how to construct the diagram for SLR1? No need to construct. Why? Same LR0 diagram can be used to check the conflicts of SLR1. That means you did the job for LR0, means you also done for SLR1. So diagram for SLR1, the DFA for SLR1 is the same that you have done for LR0, only checking the conflicts would be different. Of course, you can construct a different diagram, but not required. Now for SLR1, construct the same LR0 diagram, but check the conflicts different way. What do you mean by different way? If you want to check SR conflicts in SLR1, how do you check? Here RR conflicts, how do you check? Or RR conflict or conflicts in SLR1, how do you check? Already you know one shift item should be there and one reduced item should be there in the same state, right? In the same state. Remaining may or may not be there, it is fine. In the same state. But what is the meaning of shift item? You know it. There is a production, let us say you have some LHS arrow. Shift means somebody is there here, does not matter. Here terminal is there, that is it. Beta means I do not know who is that. Alpha, beta I do not know, but after dot terminal is there. And reduced item means somebody is there at LHS. Reduced means something here gamma, dot is at the end. So focus only on this blue. Here after dot T is there, here after dot no one is there. Do not look at who is LHS, who is alpha, beta, gamma, we do not care. In case if these 2 kinds of items are present in the same state, one is a shift, other is a reduced, then what you have to do? What you have to do? So assume this is X production, I am just naming it, but do not worry. This is, let us say, X production, this is Y production, LHS is X and Y, assume that. So what you have to look at here, this T, you need to look at the follow of this LHS. That means if T belongs to follow of Y, that follow of Y you need to compute from the grammar, then only conflict. Previously we did not look at in LR0 because it has no knowledge. That's for LR0, 0 lookouts it will look at. It is not having any knowledge, but it's SLR1. But this one is so simple. To compute the follow of Y, we don't follow the diagram, we don't follow the DFA, we look at whole grammar. From there we compute the follow of Y, follow of Y. So if this T belongs to this follow of Y, then we say that is after dot also the T is coming. Here you don't have, right? I want to know who is after, so I am going for this one. You already know how to compute the follow set. I just want to know who is after this dot. After this dot, if T comes, then there is a conflict. In case this T is not there in the follow of Y, then these two items are not producing the conflict. So shift and reduced items are present in the same state, and terminal of the shift item is present in the follow of reduced item. So after this T comes, then we have a conflict. What is RR conflict? RR means we have two reduced items. Let us say RED1, RED2, reduced items we have in the same state, What do you mean by reduced item? What do you mean by reduced item? Reduced means let us say something X derives alpha dot. Here let us say Y derives let us say alpha dot. We have two reduced items here. Only look at the dot. Dot is at the end, means it is reduced. You have seen two reduced items in the same state, then what do you do? After dot, do you have the same terminal in both of them? Anyhow we don't have a terminal, so we compute follow of X and follow of Y using the follow set knowledge. What do you compute here? If follow of X and follow of Y are having common terminals, how do you check common terminals? Intersection, follow of Y. If you see anything common, how do you say common? Follow of X intersection follow of Y is non-empty, is not empty, means there is a common terminal in both of them. Common terminal, at least one common terminal in both of them. That means after dot same terminal may come, we have a confusion. Should I reduce this or this? I am not clear, because in both of them the terminal is there. Okay, then we produce RR. So can you check now this RR conflict? Anyhow previously both are LR0, so no problem at all. Okay, previously both are LR0, so when the grammar is LR0, definitely it is SLR1, definitely it is SLR1. Okay, we are going to check this grammars later on, but understand each one how you do it. Okay, LR1 construction, LR1 construction. What is LR1 construction? You require LR1 items, right? Let me take smaller example to do it. Suppose I have S derives, very simple one, SA or SB, SB or C. Now I am going to draw a diagram for this, which may take much time, but you should know how to draw the diagram. We are going to use LR1 items, right? So we always begin with the S derives dot S in LR0, but in CLR1 and LALR1, what you do is, here you are going to keep a dollar, because you are going to maintain the look head along with the production. So we have two parts now, actual part and the look head part. That's why we have the one is very powerful in LR1 and LALR1. Okay, but in SLR1 no need to maintain that. Whenever you want you can compute from the grammar, otherwise you will waste a lot of time, a lot of space in the table or diagram. Fine, this is the first item you need to begin with. That's the initial state beginning. Now with the help of this we are going to expand. Because of this S, we will write S productions. How many are there? 3 are there. and all of them we keep the dot at the begin. All of them you need to compute its look heads. You need to compute now. Here, how do you compute the look heads of these three items? Okay, so very important. Carefully observe. If you can understand this problem, all the problems to construct the LR1 diagram would become so easy. Fine. Because of this S, have you written these three items? Yes or no? Yes. All these three you have written only because of this S. Only because of this S. Now tell me, who is after this S? Dollar. So the dollar will be maintained here. So you are going to compute the follow of this S. So in generally, how do you compute? Suppose you have x derives alpha dot y beta comma something you have, let's say anything L. That's L is a look ahead set, let's say. If I am going to write the y productions here, something I am going to write, then immediately what you do, its look heads depends on who is here, the first terminal. If beta you find any terminal here, right? If you don't have the beta, you copy this one. So very simple. Who is the first symbol comes here. Okay, so that will be maintained here. Simply I can say first of beta L. The comma is there, but the comma is just concatenation. Okay, the L is going to come after the beta. So we separate to just maintain, because L is not the part of the production, right? We computing, so we just separate with the comma. But assume that this L actually comes after the beta. Only comma we keep because we are computing L separately. So first of beta L. Clear this point? That is why the first of here beta is not there, so dollar directly will copy here. Because of this S. Now look at what I am going to do. Here we have one more S. Because of this S also, you need to write these three items again. But why should I write again? So I have already written, right? So what we do here, this A is coming just after S. That means beta is there somehow. Now this A we are going to copy in all of them. So here R A, R A, R A, or you can put in the set also if you want it. Okay. Now because of this S also, we have to write these three items again. So instead of writing again, this B we are going to keep here R, B, R, B, R, B, R, B. Okay, I hope you understood. Here C is there, so we don't expand. There are three S. All the three S are having different look heads. After that, after S dollar, after S A, after S B. That's why dollar AB is maintained for this three S. So this is the initial state. This is the initial state. If you have understood this initial state, then everything else is easy for you. Okay, let me now, I don't put these boxes, this arrows, all these things. I'll just construct. S, three productions having S, I'll keep there. One production is having C, so I'll keep here. Okay, I'll just move all these three here. S dash derives, copy paste. Dot S, now S dot, because we are reading S, comma dollar. First production, first item. Second item, S derives S dot A, S dot A, comma. Now all these things, dollar or A or B, any of these lookouts can come for this item. Now here S derives S dot B, comma dollar or A or B, dollar or A or B. Now don't close. Look at after dot no non-terminal, or no non-terminal, after dot no non-terminal, after dot no non-terminal. So now I can close. Okay, this is, let's say I1, something like that. Now when you read C here, S derives C dot, that's dollar or A or B. Fine. Taller or A or B. Now here look at dot is not at the end, right, on all of them. Here it's fine. Here A, B. So still there is something to read. So here you need to read A and you need to read B and read it. S derives SA dot. It's over now. The look at anyhow you copy paste, right? So that's dollar or A or B. Only one because dot is at the end, and here is also dot is at the end. That's over. Now here dot is already at the end. Now this is how you compute or construct the LR1 diagram or CLR1 diagram. But this diagram need not be LALR1 diagram. For constructing LALR1, you follow the same approach. But some of the states may be combined in LALR1. But same diagram will be used to construct LALR1 also. But anyhow, now let me check. Do you have any conflict in CLR1 or LR1? If you want to check conflicts, how do you do that? Here anyhow, you don't have reduced items here. Here also you don't have reduced items. Of course, acceptance is there, but no reduced. Here, one item. So anyhow, there is no conflict to check. But in case if you find any conflict, how it looks like? Let me show that. Conflicts in LR1. If you see SR conflict in CLR1, even LALR1 also same rule, but diagram only may differ sometimes. SR conflict, how do you check? You have a shift item. S means shift item. You have reduced item. Everything is there here itself. In the shift item, what do you see? Something like, right, x derives alpha dot t beta. Let's say comma, you have L1, some lookup set. Here you have, let's say, y derives reduced item, right, gamma dot comma L2. So this is about SR conflict. If both are present in same state, then how do you look at this t? Previously you were looking at fall of y, now fall of y already there. Just look at here. If t belongs to L2, that set, then we say it is a conflict, otherwise no conflict. There is here t present, then you get a conflict. Previously in SLR1, if t belongs to fall of y already there in CLR1, even LALR1 also same rule. So this is very easy to check because everything is computed here only. The lookouts that follow us already computed based on the paths. That's why it's so easy to check the conflicts. What about RR conflicts? It is also so easy. If you want to check RR conflict, you tell me what are the reduced items. You have one reduced item, let's say red 1, reduced 2. What is that item? Let me say one is x derives alpha dot, another one y derives alpha dot. So you have something here like L1, L2. So now these two are present in the same state, remaining may or may not present. This L1 and L2 are having the common items or common terminals, or not items, common terminals. Then we have conflict. What is that? If L1 intersection L2 is non-empty, then definitely there is a terminal present commonly to these two items. Okay, these are the conflicts for CLR1 as well as LALR1. Okay. Now, how do you construct LALR1? Very simple. First, step 1, construct CLR1 DFA. Step 2, combine states if they have same set of items including the dot, same set of items but ignore the lookheads. Same set of items where lookheads may differ, we don't care, where lookheads may be different. Still you need to combine. Example, how do we combine? Suppose a simple example, okay, don't worry about actual grammar. Here something like you have A derives let's say A dot B comma let's say dollar. Another one you have, let's say B derives A dot comma let's say C, and these two items are there. And when I come here, let's say I have same item, but what I may have, let's say D you have, B derives let's say A dot, maybe you have C, I don't care, same or different. See here, these two are actually two different states in CLR1, but when it comes to LALR1, these two even same items are there, two items, and dot is also exactly same position, only lookouts are different. Then what you do is, these two states we are going to combine. We are going to combine. How do we combine these two states? Let's say this is let's say I5 and let's say this is I7. Simply what you make a new state, let's say I57. Just together is a one state, that's all. You combine. How do you combine? Item is same anyhow, A derives A dot B, A derives A dot B comma, another one B derives A dot. But how do you combine now? Just dollar and D you combine, so that you will get dollar or D. And another one C, C, both are same, right? Just write one C, fine. That's it. This is the new state. This state you will get in LALR1, but these two states are there in LALR1, sorry, CLR1. In CLR1 you have these two states, then combine into one state in LALR1. But when you combine, you may get a conflict, that's fine. You may get a conflict, but most of the grammars you see depends on the type of the grammar. That grammars especially used for the programming languages like C, C++, some other syntax oriented programming languages, LALR1 would be sufficient to implement the compiler. That's why LALR1 was so popular, to save the space. Because when you are combining here, you need two rows separately in the table. Now you have only one row. That means you are saving the space basically. Okay, this is about LALR1. Now, do you get any conflict? You see here, suppose this is SR, this is SR. Okay, yes, it is SR, right? The shift item, reduced item, shift item, reduced item. And here no conflict. Yes, no conflict means B is not present here. Here also B is not present. See here, B is not present, B is not present. Will the B present here? Never, because same thing is coming there also, right? So SR conflict never happens when you combine. Here no SR conflict, no SR conflict. That is, this in this grammar you don't have SR conflict for CLR1. When you combine, you will never have SR conflict in LALR1. But you may get RR conflict. Why? Because in RR, let's say you have B A dot. Here let's say A derives A dot. Here you may have different symbols. Here you may have a different symbols. But this symbol may match with this symbol in cross. Example, suppose something like this. A derives A dot. You have let's say X. B derives A dot. You may have Y. Both are different. So no conflict in this state. And another state in CLR1 I am saying A derives A dot. B derives A dot. This Y is not there here, but it may be here, right? Let's say Z. Now when you combine, this is in CLR1 or in LR1, we don't have a conflict. But when you combine into one state in LALR1, what do you get here? A derives A dot, B derives A dot. Here X or Y. Here Y, Z. See that? You got a common terminal. Intersection of X comma Y and Y comma Z, you will see there is a Y common. So here you will get a conflict. So here RR conflict possible, RR conflict in LALR1. But what you don't have, there is no RR in CLR1 here, but you got RR conflict. There is a possibility. That means when you combine the states of CLR1, there is a possibility of RR conflict in LALR1, but you will never get SR conflict. This point is very important for the exam. So you can note down that point. You may get RR, but you will never get SR conflict in LALR1 when you combine the states of CLR1. How do you check? Same. Checking is same as LR1. Only the thing is diagram is different. You may combine, but the way you check is same. Conflict checking is same as CLR1. Now, this is a very important theoretical points. What are the theoretical points you are going to learn is really going to help you for exam. Of course, there are many theoretical points. Without consulting the table, without knowing the algorithm, also you can answer them. But if you do them, you can remember for a long time. Okay, I'm going to write many of these points. First point, when you check the parsers, the LR0 parser is less powerful than SLR1 parser, less powerful than LALR1 parser, and less powerful than CLR1 parser. Okay, who is more powerful here? CLR1. Fine. Second point, when you look at the grammars, the set of LR0 context free grammars, it's a one set. This set is strictly inside a subset of set of SLR1 context free grammars. That means every LR0 you can say SLR1, but SLR1 need not be LR0. This set is definitely inside the set of LALR1 grammars. This set is strictly inside or subset of set of all LR1 or CLR1 CFGs. This is about the grammars classes relation. These four classes are actually having subset relation. And third one, if you are only talking about one grammar, you can say LR0 context free grammar is means implies. I can say SLR1 grammar implies means is. Remember is, don't use a subset word here. It is SLR1. Every SLR1 is LALR1. This is a context free one grammar I am talking about, and that implies LR1 grammar. And when the grammar is all of them, definitely this grammar is always going to be unambiguous. Unambiguous, no need to be this one. But once you have answered this is, let's say LR0, means it is definitely unambiguous. If you answer SLR1, it is also unambiguous. But unambiguous need not be LR1, unambiguous need not be LALR1, CLR1 need not be LALR1, but every LALR1 is CLR1. So one direction is holds, a converse direction may or may not. The fourth one, when you talk about the table, especially table, the table also depends on number of states. So I am just writing n represent number of states, also called as number of rows in the table. N of LR0 table or LR0 DFA is equal to n of, n means number of states. You write it, n represent here number of states. N of SLR1 DFA. If you want a table, n represent number of rows, which is equal to number of states in LALR of 1. Same for the same grammar we are talking about. Comparison of all these four parsers for the same grammar. Okay, here in this fourth point, number of states in, okay, this one is less than or equal to. Even though these three are equal all the time, but the CLR1 may have more number of states or equal to others. CLR1 or DFA, that's diagram. It's a very, very important relation in terms of the state diagram. These three will have the same number of states, but this one may have more or equal to this three. Fifth point, when you look at the tables, these three tables you can build the with the same size, but this table size may be bigger because of many states. You will get many rows. I can say the table size, I'll just mention LR0 table, right? I'm just mentioning like this, assume it is size of the table, which is equal to, entries may differ again. You may have more entries here, you may have less entries, that's fine, but size would be same. LALR1 table size less than or equal to size of LR1 table. Like this, you have lot of relations between this four parsers, fine. And this three, especially when you look at many things are going to match, like number of shift entries in this three will be same. Likewise, you will see number of go to entries will be same for this three, but number of reduced entries may differ in this three. Okay, anyhow, that you can't compare because that may have the bigger, that will be having sometimes bigger size compared to other three. These are the very, very important points in exam point of view. You see a lot of questions only from this slide, so keep this point and note down this slide, all the points, and if you want any extra points, you note down this 6th and 7th and so on 8th, right? Whatever the points you see between these four, please note down all of them. Okay. The last topic in this bottom-up parsing is operator precedence parser. Right, this operator precedence parser will help us, you know, when you have any operator like x plus y plus z, then you know, precedence is very important, right? How the precedence is calculated, many ways. Once you have the parse tree, with the parse tree also you can construct, depends on how the parse tree is constructed, or you can maintain a table to tell what kind of precedence it is. If it is following left to right, you know, this is going to be derived first. Like how it is going to be, like grammar might be something like a plus b, and a might be x plus y and b might be z. It's fine. See, this is going to be evaluated first if you want to do this plus. That means it follows left to right. The various concept in this operator precedence parser, but we'll look at very simple manner, you know, for the exam point of view. If you really want to learn this, it may take even more than 10 hours to just learn what is operator precedence parser. Okay, let me talk very important concepts. First one is, what is operator grammar? Asked 3 times so far in the exam. What is operator grammar? What is operator grammar? What is operator grammar? In the production, you should never see 2 consecutive non-terminals. And the second, you should never see a null production, also called as null rule. So this operator grammar, it is actually a context-free grammar, never contains, in any production you see, never contains 2 consecutive non-terminals. 2 consecutive non-terminals, and also no null production, and also no null production in the grammar. Okay, in any production you should never see 2 consecutive non-terminals and no null rule in the grammar. So if these 2 points are satisfied in the grammar, that context free grammar is called as operator grammar. Examples. See, if I write S derives AB, gone. It's not operator grammar at all. Why? Because you see 2 consecutive non-terminals, so it is not operator grammar. It is not operator grammar. Then let me check another one. S derives AAB. and A derives epsilon, B derives A. Again it is not operator because null production is there. Even the two consecutive non-terminals are not there, but null production is there. So this is also not operator grammar. Then who is the operator grammar? Something like E derives E plus E. E derives ID. Good. You never see, you don't have a null rule, you don't have two consecutive. These are not consecutive, it's in between operator is coming. This is operator grammar. Okay. Sometimes you may have something like S derives AAB and A derives B, B derives C, or let's say D, and this is also operator grammar. What is operator grammar? You should not have null production and you should never see two non-terminals consecutively. That's all. And why do we need this? Because if you want to compare two operators, in between somebody should come or no one, that would be fine. But if you look at why we do this, see, if you assume this A is the operator, assume this is binary operator, then you might be putting with epsilon. So you might be failing to represent binary operator. So why we are avoiding this? Because in expressions we have the operators and operands. To understand its behavior, this rule is going to help us a lot. So always don't keep two consecutive non-terminals, and that may give some different meaning. It may come, two operands may come without operator. That might be the one problem. And because of null rule, you might miss operands. So this is a very, very important to write the operator grammar. This operator grammar may be ambiguous or may be unambiguous. That would be fine, right? This operator grammar has nothing to do with the LR grammars. Okay, no relation between LR grammars and operator grammars. Okay, in this operator grammar, okay, we have seen the operator grammar, right? In this operator grammar, we learn operator precedence grammar. Operator precedence grammar. What is this operator precedence grammar? What is this operator precedence grammar? If you want to write operator precedence grammar, first you should take operator grammar. It is what? Operator grammar. But also it's going to have some precedence relations, provided either explicitly or implicitly. Either explicitly or implicitly. Then what is this explicit, implicit? If it is given, no issue with that, you can follow. If not given, in the grammar you can compute. That means implicit. Implicit in the sense the given grammar could be unambiguous. That is the reason you can compute. Explicitly given means given grammar might be ambiguous, so they will provide you, so you follow it. Okay, so it's one of the important point. Example I can give you: E derives E plus E or E star E or ID. Here you can't compute the precedence rules. If you try to compute it, you'll get multiple answers. Plus sometimes you see left associative, sometimes you see right associative because of ambiguity. This is ambiguous grammar. Along with this, if anybody provides some rules, okay, plus is left associative, then you will follow that only. You will never follow right associative. If anybody says star is left associative, we will always follow left associative. So along with this grammar, if I provide explicitly some rules, you can follow them. But sometimes I no need to tell you what is the associative and what is the precedence and so on. Okay, I'm missing a lot of things here. Sometimes look at here, E derives T, or let me say something, E plus T, or A and T star F or B, and F derives, let's say, C. For this grammar, this is not ambiguous, so it is unambiguous. Now I no need to tell you what is the relation between plus and plus. It follows some only one, either left or right. With the grammar you can compute. Here you can compute. We can compute. No need to give explicitly. We can compute precedence rules here. Associativity and who is having more precedence, less precedence. So this is one of the important point why we use operator precedence grammars. So you might be given with some rules, you follow them, or you can compute from the grammar. For the exam point of view, this grammar is important. We don't ask these grammars because multiple answers comes here. Okay, ambiguity is there in the answers itself. So we need to provide the extra rules. Then why we prefer this grammar? Because very simple to write. This take a lot of space. So instead of writing so many productions, we just write few productions and we'll tell what to follow. We do that blindly. Okay, we do that. Like star is highest and plus is lowest. If I am mentioning it, you need to follow that rules. Okay, if I want to convert this unambiguous to ambiguous, you may take much time to do that, right? You need to take care of a lot of things here, associativity and precedence rules. Okay, we have example here, but before this example, let me explain what are the things we have. Okay, there are three types of precedences, right? One, we have, if you have left and right operators, one is called as lesser. That means LR, assume that suppose you are writing expression x plus y star z. Here this plus I am assuming left, this star I am assuming right. Okay, suppose sometimes x plus y plus z, very important, this plus is left, this plus is right. Always we follow left right scanning. When you are following left right scanning, this left plus and right star going to be very important. Here left plus, right plus, so always important. Why? The left things will be available on the stack, right thing is still there in the input, we are comparing at that time. Okay, so right we are comparing with the left, in the sense right is there in the input, left actually there on the stack. So that order is preserved. So that's why we always specify L and R, doesn't matter what symbol L and what symbol R. We remember L means on the stack, R means on the input. Okay, that's how the parser can do comparison. Fine. It means L means left. Okay, L is having lesser or less precedence to R or than R. To means I am making an order. Of course, than also you can write. But by this English, in English you may speak R is having highest, L is having lowest. But by looking at the grammar you should know who comes first, who comes next. L comes first in the expression and R comes next to the L. And next one, similarly you can understand L greater than R means L is having more precedence than R. Another one, L is having equal precedence to R. 2 is the better than, using than word. So L is having lesser precedence to R and L is having higher precedence to R and L is having equal precedence to R. 2 means I am making an order basically. Fine. So these are the three kinds of precedences. When you have equal precedence, we don't keep, most of the times we will convert them into left or right associative. But sometimes we may read it, we will write. And other two things, associativity. They are also precedence rules, but this associativity will use when you have equal precedence. Like when you have equal precedence, there are two kinds of associativity, left and right associativity. Left means left to right, right means right to left. When do we use left associativity? If you want to give more precedence to the left operator. When do you want to use right associativity? When you want to give more precedence to the right operator. Okay, so these are also important. Here what happens? Same operator, right? Left, right? I'm just saying x is both are equal right here. When we say left associativity, the left operator has more precedence than right. That's why left associativity. We already know the L is actually equal to R. Because of this, we are doing left is more precedence. Here right is more precedence, so L is less than R. So look at that. The right has more precedence. If you want to see examples for each one, you can. At this point, very simple, like 2 plus 3 star 5. Now you see this is L, this is R. You observe that way. This is L and this is R. Definitely the plus is having lesser precedence than star. That is the situation. And for this, 2 star 3 plus 5, and star is left and this plus is right, and definitely L is greater than R. When do you get this situation? When you have something like 2 like this. This is left operator, this is right operator. We know left is equal to the right, but never say that right parenthesis is equal to left. You can't say like right is equal to left. You can't do that way. Okay, the order is very important. Left is equal to right. Now when do you get this situation? Suppose you have 2 plus 3 plus 5. This is the left. In C program, this left greater than right. This left plus is greater than right plus. And when do you get this situation? You take the dereference operators. Like when you write star star P, then actually this means left, this means right. So first you evaluate this star, so left less than star, so this is evaluated first, then this one. Okay, so right operator has more precedence here. Anyhow, these are the things you need to learn from the operator precedence parsing. That's why we are going to look at one beautiful example. Of course, we have more examples. How do you compute the relation between the operators? In the exam, they may ask only between 2 operators, or maybe 4 operators will be given. Each option will have a different comparison. Okay, you might be comparing with one with other, so you should know which one you want to compare with other operator. And I just want to think about each possibility. Okay, here how many operators are there? Minus, plus, star, hash. Okay, that many operators. I'm going to maintain a table. How many rows and columns? 1, 2, 3, 4. I'm going to maintain 4 rows. Let's say starting from here. After this, first row, second row, and third row. And then let's say this is a header. 1, 2, then 3. So I'm going to use something here. Okay, this is for heading. Fine. Let me use here the heading is for minus, plus, star, and hash. Here minus, plus, star, and hash. So this table we have to fill. What is the relation between these two? Always remember, these are the left operators. If you miss this concept, we can't get anything. So these are the right operators. Always you have to assume this while computing. If you switch left right, then answer is you don't get the proper answer here. Now you need to know how to compute these things. Okay, when you assume left operator, the right operator should come from right side only. When you assume it is right, the left operator should come from left side. That's all you have to think. With that, your answer is over. Let me check one. Minus and minus I want to check. You need to go to the production, take the minus production. If there are many, each one you have to try. So I'll go for this one. Why I'm going for this one? Because I want to compare minus and minus. Now you have two choices. Which minus you want to fix? Left or right? Left or right? This is the left one, this is the right one. Okay. If you assume this is minus is left, very simple. I am assuming this is left. Now right minus should come from the right side. So will that B gives minus? Check. B to A plus B, B to A, you can't go back to S. That is not possible. Okay, now I fixed L. I am not able to get right minus from the right side. Now what I do is, I'll assume this is the right. Now my next question is, this left minus, will I get from the left? Left who is there? S. From S, can I get, okay, I'm just writing here, S minus B. From this S, can I get another minus? Yes. From S, I can put S minus B. Now you see, when I have this right minus, I can get left minus from the left side. That means the minus following left right associativity. Without this minus, you can't evaluate that minus. So minus is left associative. Okay, this point is very important. See the order, what's happening. The left minus is having more precedence than right minus. So here how do you say now? Left minus is having more precedence. See that what's happened actually. You can see sometimes without doing anything you can get the answer. Why? Actually S is following left recursion. When it is following left recursion, the operator whoever is here, it follows left associativity. Okay. But also having right recursion, it will create ambiguity. Remember that too. So left recursion, so left associativity means left minus will have more precedence. So this minus is having more precedence than that minus. Clear this point? Left minus has more precedence than right minus. Okay, let's go for another one to think about. Now I want to compare minus and plus. Again, minus plus, I don't care which symbol, always assume left and right. This should be on the stack, this should be on the input tape, so that we can compare stack and input symbol. Now which one you want to assume? Left operator, right operator, you decide. I want to fix left here. Who is left? Minus. So if you fix the minus, now think about the plus will you get from the right. That's all. Don't think plus will come from the left or not, because for that you have a different combination here. Okay. So now let's say left is fixed here. This is the left. Here you have a left. And can you get the plus from right side? That's all. From B, can you get right? From B, can you get plus? Yes, B derives A plus B. That means that plus has more precedence, because when you write S minus B and B is giving A plus B, definitely plus has more precedence. That means minus less than plus. Always speak in left right direction. Minus less than plus. So minus less than plus. But job is not over. You only taken the minus production, you tried plus from the right. But also you should take the plus production. Where is the plus? Here. And try, is that minus left possible from left side? From A, do you get minus? No. That's why I concluded only this is the right answer. In case from A, if you get a minus, this says that minus greater than plus, but both contradicts. Okay, that's very important. From A, I don't get minus. That means this one only maintains a relation between minus followed by plus. After minus plus comes, this one only maintains a relation. Okay, so we got a relation less than. Similarly, you compute between every two and keep on doing it for some time. After computing 10 or 15 times, you don't need to write anything. With this only you can do it. See here, minus and star. Okay, this is minus, let's say left. And can I get the star, that's right, from the B? From the B, can I get a multiplication? Say B to A and A to A star D. That is, you will get it. From B, you will get this star. The star has more precedence because that's bottom present, without bottom you can't evaluate this minus, so star has more precedence. This is the right. So left is less than right, so you get less than, but write it, but look for is there any possibility of greater also, sometimes maybe. Okay, this is one job. Another one, you fix the left, you got that answer. Now fix the right. What is the right here? Star. So this is the right. Now when the star is fixed, can you get the minus from this A? No, you can't get a minus from this A. There is no relation here. There's only one relation you derived, minus and minus when it is left side, star is right side. You got only one relation, star has highest. Star has highest. Now minus and ash. So which one you want to fix? Let's say minus here. When minus is left, then can you get the ash from right side? From this B, can you get ash? See that symbol? Okay, B, when you go down, you can't get that ash. So anyhow, this is not possible. And let's say right side, this one, right operator is ash. Can you get from here minus from S? Can you get minus? Yes, S minus B by putting this production. It means you have a left operator has more precedence than right. So you get this one. Okay, I filled one row. You just try to fill another one. But after filling this row, every row, very, very interesting points will come out from here. Okay, this is homework for you. You just keep doing it. But I'll tell you one thing. See, minus, minus, that's going to give you associativity, because minus, minus is having same precedence. Plus, plus, it gives associativity. But how to find? See, left minus has greater than right minus. Means left side is more, means left associativity. In case if you see minus, in case less than, left minus is less than right minus, that means right operator has more precedence. That means right associativity. So if you are going to see something like x here, of course x means here, let's say left operator, this one, this is a right operator. Then if you see the left less than right, means right has more precedence. If you see left greater than right, means it follows left associativity. So you can compute from here left associativity and right associativity. Okay, I hope you can do it. We have a lot of homework questions here. Please do it. I'm giving homework, many questions. This will help you to practice for the exam. Homework. But remember, if the grammar is ambiguous, you get multiple answers, and for that you need to give additional rules which one to follow. Okay, in case if you find ambiguity, you get multiple answers, so be careful about it. So with this we have almost completed this whole parsing, but you know, I have tried to cover most of the concepts which are required for the gate. Still, if I ignore few things, you require to practice them, but always believe, look at the previous year gate questions. I have tried to cover the most of the concepts of them to, you know, that will ensure so that you will be ready for the next coming exam. Here what is more important, grammars, various grammars we have learned. You need to identify like the L1 grammar, LR0 grammar, SLR1 grammar, and LALR1 grammar, and CLR1 grammar. It's one of the important, including unambiguous. You need to identify this grammar also, and ambiguous CFG. Apart from this, any other grammar that you have seen, left recursive grammar, you have to identify if the grammar has left recursion. So various types of grammars we have learnt up, and then we have also seen LL1 table. Before that we computed first set and follow set. In the exam you will see them directly, right? We have also seen constructing the DFA, but actually you don't need them. For exam point of view, closure set, you need to compute closure function or closure set you can say, and go to set. These two sets you should know how to compute with the help of the items. Okay, these are the main topics you should know, and relation between these various parsers. That's all, I hope, which will help you to crack the compiler questions, most of the compiler questions. Yeah, thank you so much for watching this whole syntax analysis. In the next coming video, we'll be learning a lot about syntax directed translations. In case if you see, if you have any doubts while watching this video, you may ask the questions in the comment section. If I get the notification, definitely I'll try to reply to you. Thank you so much.